Think about what you believe you know about the biggest things in our universe. For most of us, size feels straightforward, something we can measure and compare easily. Yet when astronomers first began studying the largest stars, they discovered that reality was far stranger than anyone expected. Stars so enormous that our entire solar system could fit within their glowing atmosphere, objects that challenge not just our sense of scale, but our understanding of what's even possible. The universe has a way of making our assumptions look small, constantly surprising scientists who thought they had figured out the rules. Over time, what seemed impossible has become routine discovery, and what felt like the absolute limit keeps getting pushed further. We'll be exploring these cosmic giants in this video and learning just how vast and surprising our universe truly is. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. When we think about stars, most of us picture something roughly like our sun, a familiar bright dot in the sky, warm on our faces during summer afternoons. But the sun, as it turns out, is actually quite ordinary in the grand scheme of things. In fact, compared to the true giants lurking out in space, our sun is practically tiny. There's something deeply humbling about that realization. The very thing that makes life possible on Earth, the source of all our warmth and light, is just a middle-sized star among billions of others. It makes you wonder what else we might be getting wrong about our place in the cosmos. Stars begin their lives in much the same way, regardless of how large they'll eventually become. Picture a vast cloud of gas and dust, cold and dark, drifting silently through space. Gravity slowly pulls this material together, bit by bit, over millions of years. As the cloud contracts, it heats up. Eventually, the center becomes so hot and dense that hydrogen atoms start fusing into helium. That's when a star is born, and that fusion process is what keeps it shining. Most stars settle into a comfortable middle age, burning steadily for billions of years. But some stars are different from the very beginning. They start with so much material, so much mass, that their entire life story unfolds differently. These are the stars that will eventually become the true giants. The curious thing about stellar giants is that they weren't always so enormous. Many of them actually began as relatively compact, incredibly hot blue stars. But as they age, something remarkable happens. Their outer layers start to expand, puffing outward like a slow-motion balloon. The star grows larger and larger, sometimes reaching sizes that seem almost impossible. Imagine a star so vast that if you placed it where our sun sits now, its surface would stretch past the orbit of Mars. Some of these giants would engulf Jupiter. The most extreme examples might even reach out to Saturn's orbit. Light itself, traveling at 300,000 kilometers per second, would take hours to cross from one side of such a star to the other. That last fact is worth sitting with for a moment. Light, the fastest thing in the universe, needing hours just to travel across a single star. It's one of those details that forces you to completely recalibrate your sense of scale. These stellar behemoths belong to a category astronomers call red supergiants and hypergiants. The red part comes from their surface temperature. As a star expands to enormous size, its outer layers actually cool down, giving off that characteristic reddish glow. It's counterintuitive, but the bigger these stars get, the cooler their surfaces become, even though their cores remain unimaginably hot. Some of the most famous examples have names that sound almost mythological. Betelgeuse, the red supergiant that forms the shoulder of the constellation Orion, is one that many people recognize. Then there's Antares, whose name literally means rival of Mars because of its reddish color. And there's UI Scuti, which for a while held the record as the largest known star by radius. But here's where things get interesting from a scientific perspective. The title of largest star isn't fixed forever. As our telescopes improve and our measurement techniques get better, we sometimes discover that our previous estimates were wrong. What we thought was the biggest star might get dethroned by a new discovery, or we might realize we overestimated its size in the first place. This uncertainty isn't a flaw in science. It's actually one of its greatest strengths. Astronomers approach these extreme objects with a healthy mixture of excitement and skepticism. When you're dealing with something so far away and so unlike anything in our everyday experience, getting accurate measurements becomes incredibly challenging. The distances involved are part of what makes this so difficult. These giant stars are thousands of light years away from us. That means the light we see from them left the star thousands of years ago. We're essentially looking back in time, trying to measure something that might have already changed dramatically since the light began its journey toward Earth. There's also the question of what we mean by size when we're talking about stars. Unlike planets, which have fairly well-defined surfaces, stars don't have sharp edges. They fade gradually from their dense cores out to their thin outer atmospheres. Deciding exactly where a star ends and empty space begins requires making some arbitrary choices about density and temperature. This is why you might see different numbers for the same star's size, depending on which source you're reading. It's not that anyone is wrong. Exactly. It's more that they're using slightly different definitions or measurement techniques. The physics of how these giants can exist at all is fascinating in itself. You might think that gravity would simply crush such an enormous star under its own weight. And in a sense, that's exactly what's happening. Gravity is constantly trying to compress the star, while the energy from nuclear fusion in the core pushes outward, trying to make it expand. For most of a star's life, these forces balance each other perfectly. But as a star ages and starts running low on hydrogen fuel in its core, that balance begins to shift. The star starts fusing heavier elements, which changes the energy output. Sometimes this causes the outer layers to expand dramatically, creating the giants we observe today. This expansion phase doesn't last forever, though. These enormous stars are actually quite unstable. Compared to smaller, longer-lived stars like our Sun, they might exist in their giant phase for only a few million years, which is practically an instant in cosmic terms. Eventually, many of these stellar behemoths will end their lives in spectacular fashion. The largest ones are destined to explode as supernovas, events so energetic they can briefly outshine entire galaxies. When that happens, the star's outer layers get blasted into space, seeding the surrounding region with heavy elements that will eventually become part of new stars and planets. It's a reminder that even the most enormous, seemingly permanent objects in the universe are temporary. These giants that dwarf our entire solar system will eventually burn out, explode, or collapse into something completely different. In their destruction, they'll create the raw materials for future generations of stars. There's something poetic about that cycle. The largest stars in the universe, these cosmic behemoths that stretch our imagination to its limits, are also the ones most willing to sacrifice themselves for what comes next. They live fast, burn bright, and go out in a blaze of glory that enriches the entire galaxy. The numbers we use to describe stars, those millions and billions of kilometers, they start to feel empty after a while. They're so far beyond anything we know from walking around our neighborhoods that they lose their grip on reality. Think of the sun as something you could hold, maybe the size of a basketball. Earth becomes a tiny seed, circling at the distance of a few car lengths. Jupiter turns into something like a marble, rolling much farther away in this miniature solar system. Now picture swapping out that basketball for something enormous, maybe the size of a city block, or an entire mountain range. At some point, your mind just stops being able to picture it clearly. Not because it's complicated, but because nothing in our daily world gives us practice with these scales. The universe operates on these impossible sizes, and there's something oddly comforting about that fact. We're small in comparison, undeniably, but we're also clever enough to figure it out, bit by bit, just by paying attention and thinking it through. Giant stars don't show up very often in our galaxy. Most stars out there are actually quite small, dim red dwarfs that barely glow compared to our sun. The massive ones are the unusual cases, burning through their fuel at incredible rates, living fast and dying in spectacular explosions. They're like cosmic fireworks, brief and brilliant against the long, slow background of smaller stars. When astronomers spot one of these giants, it becomes an immediate target for intense observation. Telescopes examine them across different types of light, visible and infrared, and beyond. Scientists measure brightness, temperature, distance, then use all those pieces to estimate size. But figuring out how big a star is when it's hundreds or thousands of light years away, that's genuinely difficult work. Even our most powerful telescopes often can't make out the surface details clearly. Instead, astronomers use indirect methods, combining various measurements to infer the size. Sometimes those estimates get revised. A star once thought to be the largest known might get bumped down, or a new discovery might claim the title. So when we ask about the largest star in the universe, the honest answer is usually something like, as far as we know right now. Science is comfortable with that uncertainty. It leaves space for new discoveries, new surprises, waiting out there in the dark. Right now, while you're listening to this, there are stars glowing steadily that are larger than anything our minds naturally picture. Light from these distant giants travels across vast empty spaces, sometimes for thousands of years, sometimes millions, before it reaches our telescopes and cameras. In a way, studying stars is like listening to very old echoes. We're hearing stories that started long before any of us existed, stories written in light that are still arriving, still unfolding as we watch. When people first learn about the largest star in the universe, it sounds straightforward. Bigger should just mean bigger, right? We measure size all the time. A bigger house has more rooms. A bigger animal weighs more. It seems natural to think that stars work the same way, that the biggest star is simply the one with the most material, or the one that looks largest in the sky. But once astronomers began studying stars carefully, they discovered that the word largest becomes much more complicated than it sounds. Different stars can claim the title depending on exactly what you're measuring. To understand why, it helps to think about what a star actually is. A star isn't a solid object like a rock or a planet. It doesn't have a surface you could land on, or a clear boundary where the star ends and space begins. Instead, it's a massive sphere of hot gas, mostly hydrogen and helium, held together by its own gravity and powered by nuclear fusion happening deep in its core. The outer layers of that gas gradually thin out as you move away from the center, fading into space rather than stopping suddenly. When astronomers talk about a star's size, they're already making a choice about where to draw the line, where to say this is the edge. Usually they define size by radius, the distance from the center to the layer where the gas becomes thin enough that light can escape freely. This layer is called the photosphere. It's what we see as the visible surface, even though it's not solid at all. That definition works well for most stars, but for extremely large ones, especially red supergiants and hypergiants, the outer atmosphere can be so extended and wispy that finding the exact boundary becomes tricky. The outer layers might be drifting outward, forming a hazy envelope rather than a neat sphere. Right from the start, measuring size involves some interpretation. When astronomers describe a star as large, they're usually talking about radius, not mass. Those two things can be surprisingly different. Mass is simply how much material the star contains. Our Sun has a mass of about 2 trillion kilograms. That number is so enormous it's hard to grasp, but in astronomy, it serves as a useful reference point. Scientists often compare other stars to the Sun using solar masses. A star with 10 times the Sun's mass gets described as having 10 solar masses. There are stars with dozens, even hundreds of solar masses. These are among the most massive stars known. They burn incredibly brightly and live very short lives. But here's the surprising part. Some of the largest stars in terms of diameter are not the most massive. Many of them actually contain less mass than some smaller, hotter stars. That might seem strange at first, but it makes sense if you think about the difference between dense objects and fluffy ones. A small steel ball can weigh more than a large balloon because the balloon is mostly empty space. Similarly, a giant star can be enormous in size, but have relatively low density in its outer layers. Red supergiants are perfect examples. Their outer atmospheres are extremely expanded, stretched over enormous distances. The material there is incredibly thin, far thinner than anything we encounter on Earth. Yet gravity still holds it together as part of the star. So one way to define the largest star is by radius, the star with the greatest physical size from center to outer layers. Another way would be by mass, the star containing the most matter. And yet another way would be by luminosity, the total amount of energy the star emits. Each measurement tells a different story about what it means to be large. Luminosity is a measure of brightness, but not the brightness we see with our eyes. Astronomers distinguish between apparent brightness and intrinsic brightness. A nearby candle can look brighter than a distant lighthouse, but that doesn't mean it produces more light. To find a star's true luminosity, astronomers measure how bright it appears and combine that with its distance. Once they know how far away the star is, they can calculate how much energy it must be producing to appear as bright as it does from Earth. Some stars are incredibly luminous, millions of times brighter than the Sun. These stars may not always be the largest in diameter, but they pour out energy at rates that challenge our ability to comprehend them. The universe seems to enjoy these kinds of extremes, these scales that push against the boundaries of what we can easily picture or understand. When we talk about the most energetic objects scattered throughout our galaxy, we immediately run into a fascinating problem. The word largest suddenly becomes slippery, almost philosophical in nature. We might mean the star with the biggest radius, stretching furthest into space, or perhaps we're talking about the one with the greatest mass, packed with the most material. Then again, maybe we mean the brightest one, the star pumping out the most energy every second. Temperature adds another layer to this puzzle. So does density, that measure of how tightly packed the star's material really is. Lifetime becomes relevant too, because some stars burn bright and fast, while others simmer for billions of years. Each of these properties tells us something different about what makes a star truly impressive. The challenge deepens when we remember that stars aren't frozen sculptures in space. They're dynamic, constantly changing, evolving through different phases of existence. A star that starts life as a hot, compact ball of nuclear fire might later expand into something truly colossal. Our own sun will eventually demonstrate this transformation, swelling into a red giant hundreds of times its current size. During that expansion, something counterintuitive happens. The sun won't actually gain mass. It'll lose some of it. Material will drift away into space, carried off by stellar winds. But the radius, that distance from center to edge, will grow dramatically. This creates an interesting paradox where an older, less massive star can dwarf a younger, heavier one, simply because of where each sits in its life cycle. Picture a massive young star, dense and blazing hot, sitting next to an ancient giant that has puffed up in its old age. The younger star might contain far more material, but the older one could be vastly larger in diameter. Which one deserves the title of largest depends entirely on how we define our terms. Measuring these distant giants presents its own set of challenges, ones that might surprise you with their complexity. Most stars, even the biggest ones, appear as nothing more than points of light through our telescopes. They're simply too far away for us to see their actual disks, their true shapes and boundaries. Imagine trying to measure the size of a marble from several miles away. That's the scale of difficulty astronomers face. One clever method involves measuring both temperature and brightness. Physics provides a relationship between these properties and size. If you know how bright a star truly is and how hot its surface burns, you can calculate how large it must be to produce all that energy. It's like working backwards from the light to understand the source. This technique works well, but it depends on knowing the distance to the star. Distance measurements in astronomy are notoriously difficult, filled with uncertainties that can compound into significant errors. A small mistake in estimating how far away a star sits can lead to huge differences in calculated size. Another approach uses something called interferometry, a technique that links multiple telescopes together. This creates a virtual instrument, much larger than any single telescope, allowing astronomers to resolve the tiny disks of some nearby giant stars. Combined with distance measurements, This provides a more direct way to measure stellar dimensions. Even with multiple methods available, different techniques sometimes give different answers. When you're studying objects hundreds or thousands of light years away, small measurement errors can translate into enormous differences in estimated size. This uncertainty explains why the title of largest known star has changed hands several times over the years. New observations arrive regularly, instruments improve, data becomes more precise. The rankings shift as our understanding deepens. It's remarkably similar to how early mountain explorers made their best estimates of peak heights, only to have later surveyors with better tools revise those numbers significantly. The largest stars often aren't perfectly round either, which adds another complication to measurement. Their outer layers can be unstable, churning in massive convection currents that rise and fall like enormous slow-motion storms. Some of these giants pulsate, expanding and contracting over timescales of months or years. Others lose material steadily through stellar winds, creating shells of gas that drift outward into space. When astronomers quote a radius for one of these variable giants, they're often providing an average value rather than describing a fixed boundary. The star might be larger or smaller at any given moment, breathing in and out as physical processes play out on scales. Numbers alone often feel abstract when we're talking about objects this large. Astronomers frequently compare giant stars to our solar system to provide more intuitive scale. If a star's radius extends beyond Mars's orbit, that comparison helps us grasp the magnitude involved. Imagine placing such a star where our Sun sits now. Mercury would be inside the star's outer layers. So would Venus, Earth, and Mars. Jupiter might orbit just outside the surface, or perhaps even within those diffuse outer regions. This visualization helps make the concept more tangible. But even this comparison has limitations. The outer layers of a giant star aren't like a planet's surface. They're thin, diffuse, constantly in motion. A spacecraft entering those layers wouldn't encounter a solid boundary, but rather a gradual thickening of hot gas. The idea of being inside a star becomes more complex than it initially sounds. These measurement challenges reveal something profound about the universe itself. Rarely does it offer simple answers to big questions. Instead, it invites us to look deeper, to refine our definitions, to accept that sometimes the answer depends entirely on how we phrase the question. Astronomy becomes a patient science, progressing step by step, observation by observation, each new measurement adding another piece to an ever-expanding puzzle. Understanding what largest means naturally leads to deeper questions. How do stars grow so enormous in the first place? What conditions allow such massive objects to form? You might assume the biggest stars begin life already giant, as if the universe simply creates them that way from the start. Reality proves more gradual, and in many ways more interesting. Even the largest stars begin their existence in cold, dark, quiet regions of space, where nothing appears to be happening. These regions, called molecular clouds, stretch across dozens or hundreds of light years. They contain vast collections of gas and dust, mostly hydrogen mixed with traces of helium and heavier elements left behind by previous generations of stars. Drifting through one of these clouds wouldn't feel like moving through a cloud in any familiar sense. The gas is so thin that you'd hardly notice it. The best vacuum chambers on Earth are actually denser than parts of these stellar nurseries. Yet over enormous distances, even this faint material adds up to immense mass. Within these clouds, gravity works constantly. It's a quiet, patient force that never stops pulling. Tiny fluctuations in density, regions where gas is just slightly thicker than surrounding areas, begin to pull in more material. Over time, these regions grow denser, drawing in gas from farther away. Initially, the process moves incredibly slowly. Millions of years might pass as a small clump gradually collapses into something recognizable as a forming star. Once collapse begins in earnest, it accelerates. Gravity pulls harder as more mass gathers, the core grows hotter and denser. Eventually, the temperature at the center becomes high enough for nuclear fusion to begin. Hydrogen nuclei start fusing into helium, releasing energy that pushes outward, balancing gravity's inward pull. When these forces reach equilibrium, a star is born. This basic story applies to stars of all sizes, but forming a truly massive star requires something special. It needs an enormous reservoir of material. In most parts of a molecular cloud, there simply isn't enough mass concentrated in one place to form a very large star. The collapsing region fragments into smaller clumps, each forming a modest star rather than one giant. This fragmentation presents one of the biggest challenges in understanding how stellar titans form. The largest stars tend to form in the densest, most active star-forming regions, places where huge amounts of gas pack together and many stars form simultaneously. These stellar nurseries can be spectacular sights, glowing with light from newborn stars that illuminate surrounding gas. The Orion Nebula provides a famous example, visible to the naked eye under dark skies. Inside it, hundreds of young stars are forming, including some far larger than our Sun. Yet even Orion appears modest compared to the most extreme star-forming regions in the galaxy, where clusters of massive stars are born together in tight groups. In these crowded environments, gravity has a better chance of gathering enough material to form truly massive stars. Gas flows inward from all directions, feeding the growing protostar at the center. But a problem emerges as the forming star becomes more massive. It also becomes brighter, creating intense radiation pressure, a force produced by light streaming outward. For very massive protostars, this radiation can push away surrounding gas, effectively shutting off the material supply and limiting how large the star can grow. Astronomers long wondered whether radiation pressure might prevent stars from growing beyond a certain size altogether. Yet observations clearly show that somehow, under the right conditions, nature finds ways to build true giants. Stars can grow to become truly massive giants, sometimes reaching more than 100 times the weight of our Sun. This happens despite what seems like an impossible challenge. When a star tries to form, all that material falling inward creates incredible heat and pressure. This generates radiation so powerful it should blow everything away, stopping the star from getting any bigger. But nature finds clever ways around this problem. Instead of material just falling straight down into the growing star, it forms spinning disks. Like cosmic whirlpools, gas spirals through these disks, gradually feeding the star while something remarkable happens at the poles. Powerful jets of material shoot out from the top and bottom of the star, carrying away excess energy and momentum. These jets act like pressure release valves, clearing pathways that let more material keep flowing inward. The radiation that would normally push everything away gets channeled along these polar jets, while the disk keeps feeding the hungry star. It's an incredibly delicate dance. But when conditions align just right, stars can grow to enormous sizes. Dense star-forming regions help too. When gas clouds are packed tightly together, gravity becomes strong enough to overpower the radiation trying to push material away. The falling gas has so much momentum that it simply can't be stopped easily. These rare cosmic environments become stellar nurseries for giants. Once these massive stars finally ignite, their lives unfold in ways completely different from smaller stars like our Sun. They burn through their fuel at absolutely staggering rates. The more massive a star becomes, the higher the pressure and temperature in its core, and nuclear fusion proceeds much faster. A star 10 times our Sun's mass might shine thousands of times brighter. A star 50 times more massive burns so intensely that its entire lifetime lasts only a few million years. Compare that to our Sun's expected 10 billion year lifespan, and you realize these giants live life in fast forward. These stellar titans start their lives as compact, hot blue stars. Their surfaces reach tens of thousands of degrees, blazing with fierce, energetic light. But deep changes begin happening in their cores over time. As hydrogen fuel gets consumed, the careful balance between crushing gravity and outward pressure starts shifting. The core contracts and heats up even more, while the outer layers respond by expanding outward. The star begins to swell, sometimes dramatically. For the most massive stars, this expansion can be absolutely mind-boggling. The outer layers drift farther and farther from the center, cooling as they spread out. The star turns redder in color and grows vastly larger in size. This is how many of the biggest stars in the universe reach their incredible diameters. They're not born enormous, they grow into it as they age. The scale of this growth really challenges our imagination. Picture a star that starts life maybe 10 or 20 times larger than our Sun. Over time it expands until its radius becomes hundreds, even more than 1,000 times greater than the Sun's radius. Its outer atmosphere becomes so extended that it would completely engulf the inner planets if you placed it in our solar system. Despite this vast size, the star's outer layers become extraordinarily thin. The density there might be lower than the best vacuums we can create on Earth. The star becomes like a glowing fog, spread over an immense volume, still bound together by gravity, still shining, but stretched to an almost unimaginable scale. There's something beautifully continuous about how these massive stars form. The material that creates them isn't pristine hydrogen, left untouched since the universe began. It's been enriched by earlier generations of stars. Long ago, other massive stars lived complete lives, then died in spectacular supernova explosions, scattering heavier elements into space. Those elements mixed into molecular clouds, becoming part of new stars, planets, and eventually, living things. When a stellar titan forms today, it carries within itself the ashes of earlier stars, material that's been recycled through cosmic history. Every giant star becomes part of a long chain of creation and transformation, each generation building on the last. There's something profound about that continuity, the way the universe keeps reusing and reshaping itself. The largest stars rarely form alone. They're often members of clusters, surrounded by dozens or hundreds of smaller stars born from the same cloud. These clusters can be crowded places, with stars passing relatively close to each other, gravitationally interacting, sometimes even exchanging material. In such busy environments, stellar mergers can happen. Two massive stars in a tight binary system may spiral together and combine, forming a single, even larger star. This process might play a role in creating some of the most extreme stars we know about. Not all stellar titans are simply born large. Some may grow large through dramatic encounters long after their initial formation. All these processes help explain how stars can become massive enough to later expand into the enormous red supergiants and hypergiants that compete for the title of largest known star. Even with all these mechanisms, though, there seem to be limits. Observations suggest that stars above a certain mass, perhaps around 150 to 200 times our Sun's mass, become extremely rare or may not form at all under most conditions. Radiation pressure and stellar winds become so strong that they blow away material faster than it can be gathered. Nature appears to set an upper boundary, not a strict wall exactly, but a region where forming even larger stars becomes increasingly difficult. Still, within those limits, the universe manages to produce stars of truly astonishing scale. Stars that begin in cold, dark clouds and end as glowing giants, visible across thousands of light years. Once these titans have formed and begun to age, their stories continue in ways just as fascinating as their dramatic births. When you glance up at the night sky, most stars appear as tiny white dots, sharp and steady. But some catch your attention immediately. They glow with a warmer, deeper color, almost orange or red, and their light seems softer somehow, as if it carries a different story altogether. For thousands of years, people wondered why certain stars looked this way. Today we know many of these reddish points belong to a remarkable class called red supergiants. These are true giants in every possible sense, and understanding them opens a window into one of the universe's most dramatic transformations. Stars aren't static objects. They change over time in ways that can be hard to imagine. Most stars, including our Sun, spend the majority of their lives in what we call the main sequence phase. During this period, they steadily convert hydrogen into helium in their cores, maintaining a careful balance between the inward pull of gravity and the outward pressure from nuclear fusion. This balance keeps them roughly the same size and brightness for billions of years. But massive stars live very different lives from smaller ones. They burn through their hydrogen fuel at incredible rates, sometimes exhausting it, in just a few million years. When the hydrogen in the core starts running low, something extraordinary happens. The delicate balance that kept the star stable begins to shift. The core contracts under its own weight, heating up even further, while the outer layers begin to expand. This isn't a gentle swelling, it's a dramatic transformation. The outer layers balloon outward, growing hundreds of times larger than before. At the same time, the surface temperature drops, which changes the color of light the star produces. Instead of shining white or blue, it begins glowing red or orange. This is how a red supergiant is born, not as a newborn star, but as a mature, massive star entering a new phase of its existence. The scale of this expansion defies easy comprehension. Some red supergiants grow so large that if you replaced our Sun with one, its outer atmosphere would stretch beyond Mars, sometimes reaching nearly to Jupiter's orbit. To picture this size, imagine shrinking the Sun down to the size of a basketball. In that scale, Earth would be a tiny marble orbiting about the length of a football field away. Now replace that basketball with something the size of a large office building. Suddenly, the distances to the inner planets seem very small indeed, completely swallowed by the star's enormous outer layers. Yet despite their vast size, red supergiants aren't particularly dense. Their outer atmospheres are incredibly thin, much thinner than any air we experience on Earth. The material is spread across such an enormous volume that the star becomes, in essence, a glowing fog held together by gravity. If you could somehow journey into the outer layers of a red supergiant, you wouldn't encounter a sharp surface like you would on Earth. Instead, you'd pass gradually into thicker and hotter gas, with light glowing around you in deep shades of orange and red. The density would increase slowly as you traveled inward, creating a gradual transition rather than a clear boundary. This speaks to something profound about the nature of these objects. They exist at the edge of what we can even define as solid matter. Red supergiants are also remarkably unstable compared to stars like our Sun. While the Sun's surface appears relatively calm on large scales, red supergiants are turbulent, chaotic places. Massive convection currents churn through their outer layers, like boiling cells of gas, operating on scales that boggle the mind. On our Sun, convection cells are roughly the size of continents. On a red supergiant, a single convection cell can be larger than Earth's entire orbit. Vast regions of hot gas rise up, cool down and sink again, slowly circulating over months or years. This immense convection causes the star's brightness to vary over time, and it can lead to the ejection of material into space. Red supergiants often lose mass through steady stellar winds, streams of gas that drift away from the star and form extended shells of dust and molecules around it. These shells can stretch across distances comparable to our entire solar system, or even larger. Over time, the star sheds a significant portion of its mass this way, enriching the surrounding space with heavy elements. Those elements matter more than you might think. They will eventually become part of new stars, new planets, and perhaps even new forms of life. In a sense, red supergiants are cosmic recycling centers, taking the simple hydrogen they were born with and transforming it into the complex elements that make planets, and ultimately us, possible. Astronomers often focus on nearby examples that can be studied in detail. One of the most famous is Betelgeuse, a bright red star in the constellation Orion. Even without a telescope, it's easy to spot on a clear night. Glowing with that distinctive reddish hue, Betelgeuse is enormous, hundreds of times larger than our Sun, and it has been studied extensively over the years. Recently, it dimmed noticeably for a period, leading to widespread speculation about what might be happening. Eventually, astronomers determined that part of the dimming was caused by a cloud of dust the star itself had expelled, temporarily blocking some of its light. This event served as a reminder that red supergiants are dynamic, changing objects, not static spheres sitting quietly in space. Another well-known example is Antares in the constellation Scorpius. Like Betelgeuse, it shines with a deep red color and dwarfs our Sun in size. Modern observations have revealed enormous plumes of gas rising from its surface, extending outward for distances comparable to our solar system's size. These kinds of detailed observations have only become possible in recent decades as telescopes and imaging techniques have improved dramatically. For most of human history, red supergiants were simply bright red points in the sky, their true nature hidden by the vast distances involved. Today, astronomers can map their surfaces, study their atmospheres, and even observe the motions of gas within their outer layers. It's remarkable to think that we can now examine the detailed structure of objects so far away, the physics behind why red supergiants become so large lies in how energy moves inside the star. As the core contracts and heats up, fusion begins occurring in shells, surrounding the core rather than only at the center. This releases tremendous amounts of energy, which pushes the outer layers outward. Gravity still holds the star together, but the balance has shifted. The outer layers expand until a new equilibrium is reached, one where the star is much larger and cooler at the surface than before. But this expanded state isn't permanent. Red supergiants are living on borrowed time. Their cores continue evolving, fusing heavier and heavier elements in a sequence that eventually leads to iron. Iron cannot release energy through fusion, and when the core becomes dominated by iron, it can no longer support itself. The star's life ends in a supernova, one of the most powerful explosions in the universe. Yet that dramatic ending lies ahead in their story. For now, red supergiants represent the first stage where stars truly become colossal in size, large enough to dominate any comparison and challenge our understanding of scale. They're not the absolute largest stars known, but they're the gateway to understanding stellar giants. Many of the record-holding stars, the ones sometimes proposed as the largest of all, belong to related categories that push these same processes even further. There's something quietly fascinating about how red supergiants appear to us from Earth. Despite their immense size, they look small in the sky, mere points of light. Distance compresses everything we see. A star that could engulf our entire solar system appears no larger than a grain of sand held at arm's length. It's a humbling reminder of how vast the universe truly is, and how size alone doesn't determine what we observe. Distance also complicates measurement. Determining the radius of a red supergiant requires knowing how far away it is, how bright it actually is, and how hot its surface temperature runs. Small uncertainties in any of these measurements can lead to large differences in the estimated size. That's one reason why the list of largest known stars constantly changes. As new observations refine distances and temperatures, estimates of stellar radius shift accordingly. A star once thought to be the largest may turn out to be smaller than previously believed, while another takes its place. Science progresses in this quiet, careful way, refining numbers, checking assumptions, and gradually improving our understanding of these cosmic giants. There's also the fundamental question of how large a star can become before it becomes too unstable to maintain its structure. Red supergiants are already operating close to the limits of what stellar physics allows. Their outer layers are only loosely bound by gravity, and strong stellar winds steadily carry material away into space. Some of the most extreme examples lose mass at astonishing rates, shedding the equivalent of Earth's entire mass every few years or decades. Over long periods, this mass loss can significantly alter how the star evolves. So even as these stars expand to enormous sizes, they're simultaneously slowly dissolving, their outer layers drifting away into the cosmic void. This dual nature, immense yet fragile, captures something profound about red supergiants. They represent both the peak of stellar expansion and the beginning of the end. Massive enough to dwarf our solar system, yet delicate enough to be gradually torn apart by their own stellar winds. They exist at a fascinating intersection of scale and instability, reminding us that even the largest objects in the universe operate under constraints, and that size and permanence don't always go hand in hand. Red supergiants once seemed like the ultimate expression of stellar grandeur. These colossal stars, hundreds of times wider than our Sun, possessed atmospheres so expansive they could engulf entire solar systems. For decades, astronomers believed they had discovered nature's final word on stellar size. The universe, it appeared, had revealed its upper limits. Yet, as our instrument grew more sophisticated, as our surveys of the galaxy became more comprehensive, anomalies began to emerge. Scattered across the cosmos were stars that defied the established categories. They blazed brighter than conventional supergiants, hemorrhaged material at staggering rates, and wore enormous cloaks of expelled gas. Some even dwarfed the already immense red supergiants in sheer physical scale. These celestial outliers earned a name befitting their extreme nature: hypergiants. The designation carries specific astronomical meaning beyond its dramatic sound. A hypergiant represents a star of extraordinary luminosity, coupled with fundamental instability. These stellar behemoths constantly shed material into space, while displaying signs of rapid evolutionary change. Hypergiants rank among the galaxy's most luminous residents. Some outshine our Sun by factors of hundreds of thousands, even millions. While not every hypergiant claims the largest physical dimensions, many of the biggest known stars belong to this exclusive category. Their very existence challenges our understanding of stellar physics. The key to comprehending hypergiants lies in stellar equilibrium. Every star maintains its structure through a delicate balance between competing forces. Gravity relentlessly pulls inward, attempting to compress the stellar material. Nuclear fusion counters this collapse, generating energy that pushes outward through radiation pressure. This cosmic tug-of-war sustains stellar stability. In the most massive stars, however, this balance becomes precarious. Radiation pressure grows so intense, it nearly matches gravity's inward pull. The star exists in a state of barely contained cohesion, held together by the thinnest of margins. This fragile equilibrium breeds instability in hypergiants. Their outer layers expand and contract in chaotic rhythms. Massive eruptions periodically blast material into space, creating enormous gas clouds that once formed part of the star itself. These events unfold over thousands of years, representing gradual shedding rather than catastrophic explosions. Astronomers call them stellar outbursts, slower processes that strip away atmospheric layers piece by piece. Observing a hypergiant across extended timeframes would reveal constant transformation. Brightness fluctuates unpredictably, atmospheric boundaries shift continuously, and the surrounding environment fills with drifting debris clouds. These stars embody change itself, never static, always evolving. Immense luminosity drives another defining characteristic: powerful stellar wind. Energy streaming from hypergiant surfaces accelerates particles to tremendous velocities, creating rivers of matter flowing outward into space. These winds carry away vast quantities of stellar material throughout the star's abbreviated lifetime. Some hypergiants lose mass so rapidly they shed several solar masses worth of material before reaching their final moments. The concept seems almost paradoxical, a star gradually dissolving into the void, leaving behind expanding shells of glowing gas that persist long after the original object has transformed or vanished entirely. Eta Carinae exemplifies hypergiant behavior perfectly. This stellar system, located thousands of light years distant, suddenly blazed to extraordinary brightness during the 19th century. The Great Eruption, as astronomers named this event, expelled tremendous amounts of material into surrounding space. This ejected matter formed a spectacular homunculus nebulator, a cloud that continues expanding today, illuminated by light from its creator. Current observations reveal Eta Carinae remains unstable, still bleeding mass, still evolving unpredictably. Such events demonstrate that hypergiants exist perpetually on stability's edge, their immense properties driving them toward dramatic transformations. Not every hypergiant undergoes such spectacular outbursts, though all share this fundamental instability. Red hypergiants present cooler temperatures, but achieve enormous dimensions. Yellow and blue hypergiants burn hotter, often generating even greater luminosity, despite sometimes smaller radii. This diversity shows that hypergiants aren't defined solely by size. Rather, their extreme properties, luminosity, instability, and rapid evolution mark them as a distinct stellar class. Nevertheless, many of the largest known stars are red hypergiants. These giants expand their outer layers to truly astonishing scales, appearing deep crimson due to their relatively cool but vastly extended atmospheres. Despite lower surface temperatures, their enormous extent maintains tremendous total brightness. Measuring hypergiant dimensions present significant challenges. Their outer layers often appear irregular, featuring vast gas plumes extending into space. The boundary between star and surrounding void becomes blurred, making precise measurements nearly impossible. Where exactly does the star end and empty space begin? Astronomers rely on careful analysis of temperature, brightness, and distance, combined with sophisticated atmospheric models, to estimate stellar radii. The enormous distances to these objects, coupled with their complex atmospheric structures, introduce substantial uncertainties. Measurement revisions can dramatically alter size estimates, explaining why the identity of the largest known star occasionally changes. Despite these uncertainties, certain names repeatedly surface in discussions of stellar giants. Ui Scuti VV Cephei, VY Canis Majoris, and others regularly compete for the title of largest known star. Each possesses estimated dimensions stretching far beyond human comprehension. Some of these monsters, if placed at our solar system's center, would extend their outer layers beyond Jupiter's orbit, possibly reaching Saturn's distance. Light would require hours to traverse from one side to the other. Yet these incredible dimensions represent only temporary phases in stellar evolution. The same processes causing hypergiant expansion ultimately lead to their collapse and explosive destruction. These stars live fast and die young by cosmic standards. While our sun may shine steadily for 10 billion years, hypergiants exhaust themselves within mere millions of years. This brevity adds poignancy to their existence. Cosmic giants blazing magnificently, but briefly. Hypergiants influence their surroundings profoundly due to their extreme luminosity. Their radiation ionizes nearby gas, causing nebulae to glow brilliantly. Stellar winds carve bubbles and shells through the interstellar medium, reshaping local space. In star-forming regions, these massive objects can trigger new stellar birth by compressing nearby gas clouds. This creates a cosmic cycle where one generation of giants helps birth the next. Hypergiants aren't isolated objects but integral participants in galactic evolution, shaping and being shaped by their environments. Their deaths, through spectacular supernovae, enrich surrounding space, with heavy elements essential for planet formation and life. Hypergiant rarity makes them precious scientific targets. In a galaxy containing hundreds of billions of stars, only a tiny fraction achieve hypergiant status. They represent extremes, pushing the absolute limits of what gravity and nuclear fusion can sustain. Each discovered hypergiant provides clues about stellar physics' upper boundaries. Through hypergiant observations, astronomers learn about the fundamental forces governing all stars. These cosmic laboratories test theoretical models under the most extreme conditions nature provides. As observational capabilities continue improving, the search continues for even larger, more luminous, more extreme examples. Occasionally, new candidates emerge, stars whose estimated properties challenge existing records and reignite debates about which truly deserves the title of largest known star. Perhaps somewhere in the galaxy's depths, an even more monstrous hypergiant awaits discovery, ready to expand our understanding of stellar extremes once again. When we peer into the cosmos, certain stars keep appearing in our studies of stellar giants, like recurring characters in an unfolding story about the limits of nature itself. Each of these massive objects carries its own mysteries, its own complications, and its own role in helping us understand just how enormous a star can actually become. Take Ui Scuti, sitting thousands of light years away in a constellation called Scutum. Most people would never spot this region of sky without serious equipment. Yet it harbors something truly extraordinary. This star has grown so massive that if you somehow moved it to where our Sun sits now, its outer edges would stretch past Jupiter's orbit. Light itself, traveling at its incredible speed, would need hours just to cross from one side of this star to the other. Think about that for a moment. The very thing that reaches us from our Sun, in just 8 minutes, would take the better part of a day to traverse this stellar giant. But here's where things get interesting from a scientific perspective. Measuring these enormous stars isn't like measuring a building or even a planet. The edges of stars like WOH Scuti are fuzzy, diffuse, constantly shifting. Where exactly does the star end and empty space begin? Different instruments, different methods, even different definitions of what counts as the star's surface, all give slightly different answers. This uncertainty doesn't represent failure. In astronomy, it represents honesty about the complexities of the universe. Astronomers have learned to add careful phrases to their claims, saying things are true based on current estimates or within measurement uncertainties. There's something beautiful about this scientific humility. It acknowledges that knowledge grows, instruments improve, and our understanding becomes more refined over time. Consider WOH Canis Majoris, another famous giant residing in the constellation Canis Major. For years, this red hypergiant held the title of largest known star. Early measurements suggested truly extraordinary dimensions, and telescopic images revealed something fascinating: vast clouds of gas and dust surrounding the star, material that the star itself had thrown off into space. This star is fundamentally unstable, bleeding mass at tremendous rates. Its outer layers don't form a neat, smooth sphere. Instead, enormous plumes of gas extend outward in complex, irregular patterns. When astronomers look closely, they see knots and arcs of material drifting away, all lit up by the star's intense radiation. This messy, dynamic behavior makes measuring the star's true size remarkably complicated. Where does star end and expelled gas cloud begin? Over time, better observations led scientists to revise their estimates of WOH Canis Majoris downward somewhat. The star didn't actually shrink, our measurements just became more precise. This process reveals something profound about how science works. Knowledge doesn't arrive complete and perfect. It accumulates gradually through better tools, more data, and careful analysis. Then there's WOH G64, a red supergiant located not in our own galaxy, but in the Large Magellanic Cloud, visible from Earth's southern hemisphere. This particular giant presents unique challenges for astronomers because it's wrapped in a thick disk of dust. This dust absorbs much of the star's visible light, making it nearly invisible in normal wavelengths. But infrared observations, which can penetrate dust clouds, reveal its enormous size and incredible luminosity. Stars like WOH G64 remind us that the largest stars are often messy, complicated objects. They're not clean, perfect spheres, floating in empty space. They're dynamic systems constantly interacting with their surroundings, shedding material, wrapped in cocoons of dust and gas, from their own turbulent processes. The competition for the title of largest star shifts over time as new data arrives. Astronomers sometimes joke that it's like a rotating trophy, passed from one candidate to another as measurements improve. But beyond these record-keeping contests lies deeper scientific significance. These enormous stars teach us about fundamental limits in nature. Physics itself constrains how large a star can become. As stars expand, their outer layers become more weakly held by gravity. Radiation pressure pushes outward, while stellar winds carry material away into space. Pulsations and convection churn the atmosphere, sometimes ejecting entire shells of gas. Eventually, the star reaches a point where it simply can't maintain such enormous size. It begins losing mass more rapidly, its internal structure shifts, leading toward contraction, or the final phases of stellar evolution. This means the largest stars we observe are often in brief phases of their lives, expanded to immense sizes but destined to change relatively soon on cosmic timescales. We're catching them in temporary moments of maximum size, fleeting by astronomical standards. Distance measurements add another layer of complexity to sizing up these giants. To calculate a star's radius, astronomers must know precisely how far away it sits. Even small errors in distance translate into large errors in calculated size. Measuring cosmic distances involves sophisticated techniques: parallax for nearby objects, standard candles for more distant ones, spectroscopic analysis of stellar properties. Each method carries its own uncertainties, and for very distant stars, these uncertainties can be substantial. This is why giant star measurements always come with uncertainty ranges. A star might be listed as having a radius somewhere between 1,000 and 1,500 times our Sun's radius. Within that range, its exact ranking among other giants remains unclear, but this uncertainty isn't a scientific flaw, it's part of the honest process of gradually understanding our universe. Despite their immense sizes, these stellar giants appear as mere points of light, even through our largest telescopes. Only rarely, using advanced techniques like interferometry, have astronomers managed to resolve the actual surfaces of nearby giant stars. Even then, the resulting images aren't like crisp photographs. They're often blurry, showing uneven brightness patterns, large convection cells, and irregular shapes. These observations reveal that giant stars aren't perfectly spherical. Their surfaces constantly move, shaped by enormous currents of hot gas rising and falling. Sometimes astronomers observe giant stars actually changing shape over time, their atmospheres swelling or contracting as internal processes shift. Stars aren't static objects frozen in space. They're dynamic, evolving, and in the case of the largest ones, often highly unstable. There's something quietly humbling about how these stars challenge our sense of scale. When we learn that a star is 1,000 times larger than our Sun, the number sounds impressive but remains abstract. When we realize that Earth's entire orbit would lie deep inside such a star's atmosphere, the scale becomes more tangible. It shifts our perspective on our place in the cosmos. Our Sun, which seems so large and powerful from our viewpoint, appears modest compared to these giants. Yet our Sun itself is just one star among hundreds of billions in our galaxy alone. The universe contains structures so vast they dwarf even our solar system. Interestingly, many of the largest known stars aren't visible to naked eye observation. Some sit too far away, others hide behind dust clouds. The brightest stars in our sky aren't necessarily the largest, and the largest aren't necessarily the brightest from our earthbound perspective. This means the true giants of the universe often remain hidden, known only through careful observation with powerful instruments. As astronomical surveys continue mapping our galaxy and beyond, new candidates occasionally emerge for the title of largest star. Improved infrared observations, better distance measurements, more detailed models of stellar atmospheres, all contribute to refining our understanding. Larger stars almost certainly exist, waiting to be discovered or measured more accurately. Each of these enormous objects represent a temporary victory of nuclear fusion over gravity, matter organized into structures so vast they challenge our imagination. They remind us that the universe operates on scales far beyond daily human experience, yet remains governed by the same physical laws we can study and gradually understand. The universe contains structures so vast that even the scientists who study them every day find themselves staring at their calculations, wondering if the numbers could possibly be real. These are the stars that push beyond what seems reasonable, beyond what our minds can easily accept. When astronomers encounter measurements that feel impossible, they sometimes resort to informal names that capture their sense of awe. One such name, used quietly in research discussions, is Behemoth. It's not an official catalogue designation, but it says something important about the human reaction to encountering the truly immense. The process of measuring these stellar giants begins with three fundamental properties. Luminosity tells us how much energy the star pumps into space. Surface temperature comes from analyzing the spectrum, the rainbow of colors hidden in starlight. Distance requires careful work, combining parallax measurements with studies of stellar populations. These three pieces of information allow astronomers to calculate radius, and sometimes that radius defies belief. We're talking about stars over 1,000 times larger than our Sun. To put this in perspective, Imagine placing such a star at the center of our solar system. The star's outer layers wouldn't just reach Mars, they'd stretch past the asteroid belt, beyond Jupiter, possibly approaching Saturn. Earth's entire yearly orbit around the Sun would lie buried deep inside this star's atmosphere. The inner planets wouldn't orbit around anything. They'd exist within layers of glowing, drifting gas. Picture that for a moment, the path our planet takes each year, completely enclosed by a star. The sky wouldn't be black at night, it would glow with a dim, reddish light extending in every direction. What makes this even stranger is that despite their enormous size, these stars aren't particularly dense. The outer layers are incredibly thin, with gas densities far lower than the air we breathe, lower even than the best laboratory vacuums on Earth. The star's mass spreads across such an immense volume that it becomes almost ethereal. These aren't solid spheres, or even well-defined balls of gas. They're more like enormous glowing atmospheres held together by gravity, with edges that fade gradually into the emptiness of space. Their outer boundaries aren't sharp lines, they're gentle transitions from something to nothing. Inside these giants, convection carries energy from the core outward through rising and falling currents of hot gas. In our Sun, these convection cells are roughly continent-sized. In a star like Behemoth, a single convection cell can be larger than Earth's orbit. These vast rivers of gas rise and fall over months or years, causing the star's brightness to fluctuate in slow, irregular patterns. The loosely bound outer layers create another fascinating phenomenon. Powerful stellar winds carry material away from the star, shedding enormous quantities of gas into space. Over time, this creates a surrounding envelope of dust and molecules that can become so thick it hides the star from visible light. Astronomers must then observe in infrared wavelengths, where dust becomes transparent and the star's glow can still be detected. This is actually how many of the largest stars are studied, through infrared observations that reveal their true nature. The universe often hides its greatest wonders behind veils of dust and distance, requiring patience and clever techniques to uncover. The immense size of these stars comes with a price. They burn through their fuel rapidly. The phase where a star expands to such extreme dimensions lasts only tens of thousands of years, a brief moment compared to the millions of years it has already lived. When we observe a star at this stage, we're witnessing a relatively short chapter in its life story. This adds a quiet rarity to these observations. The universe contains countless stars, but only a tiny fraction are caught in this brief phase of extreme expansion. We're seeing something uncommon, something fleeting on cosmic timescales. The distances involved challenge our perception even further. Many of the largest known stars are thousands or tens of thousands of light years away. The light we see from them began its journey long before modern civilization existed, before electric lights or airplanes or satellites. When astronomers measure such a star, they're studying it not as it exists now, but as it was in the distant past. The star's present state, whatever it might be, won't be known until its light reaches us thousands of years in the future. We're always looking into the past, always receiving messages carried by light across immense distances. Yet despite that temporal gap, the scale of these stars still reaches us through careful measurement and patient observation. Sometimes when astronomers first calculate a candidate for the largest star, the result seems too large to believe. They check their data again, refine distance estimates, compare results with atmospheric models. Occasionally estimates are revised downward, other times they hold up under scrutiny. This careful process means the identity of the largest known star is never permanently fixed. New measurements, improved instruments, and better models can change the ranking. But regardless of which star currently holds the record, the existence of such giants reveals something fundamental about the universe. Nature creates structures on scales far beyond everyday experience, yet governed by the same physical laws that operate everywhere: gravity, pressure, radiation, nuclear fusion. The same processes that shape our sun also shape stars 1,000 times larger. There's an elegant consistency in the universe, the same rules applying from the smallest scales to the most immense. An interesting contrast emerges between size and brightness. Some of the largest stars aren't the brightest in our sky. Their enormous size is balanced by relatively cool surface temperatures, spreading their light over vast areas and shifting it toward the red and infrared parts of the spectrum. A star that could engulf our entire solar system might appear faint to the naked eye, visible only through telescopes. This contrast between immense size and modest appearance reminds us that the universe doesn't always present its greatest wonders in obvious ways. The most spectacular phenomena often require careful looking, patient observation, scientific instruments to reveal their true nature. Consider how such a star would appear if viewed from nearby. From a distance comparable to Earth's orbit, the star's disk would dominate the sky. The surface wouldn't look smooth, it would appear mottled and uneven, with enormous convection cells rising and falling, slowly glowing in deep shades of red and orange. The surrounding space would be filled with drifting clouds of gas. Illuminated by the star's light, it would be a quiet, slow-moving scene, not violent or explosive, but vast and steady. The motions would unfold over months or years, rather than seconds, operating on timescales that stretch our normal sense of how quickly things should happen. This changes how we think about time as well as size. Processes that seem slow to us, gas movements over years, gradual mass loss over centuries, these are part of the ordinary life cycle of these stars. They exist on scales of both space and time that challenge human comprehension, yet remain understandable with patience and careful thought. The density contrast within these stars creates almost contradictory properties. The core remains incredibly dense and hot, generating enormous amounts of energy through nuclear fusion. But that energy must travel through layers that become increasingly thin toward the surface, creating temperature gradients that span thousands of degrees across the star's radius. These giants also challenge our understanding of stellar evolution. How does a star maintain such a tenuous outer atmosphere while still generating energy in its core? The balance between radiation pressure pushing outward and gravity pulling inward becomes incredibly delicate. Small changes in either force could dramatically alter the star's structure. The study of these massive stars also reveals something about the limits of stellar formation. There appears to be an upper limit to how large a star can become while still maintaining nuclear fusion in its core. Beyond a certain point, radiation pressure would overcome gravity entirely, preventing the star from holding together. Perhaps most remarkable is how studying these stars stretches our sense of scale without breaking our understanding of physics. They operate according to the same principles as smaller stars, just pushed to extremes we rarely encounter. They remind us that the universe is far stranger and more varied than our everyday experience suggests, yet still comprehensible through careful observation and scientific reasoning. When we look up at the night sky, we see thousands of tiny points of light scattered across the darkness. Each one of those points is actually a massive ball of burning gas, some so enormous they could swallow our entire solar system. But here's the thing that really gets you thinking. We can't actually see the surfaces of these distant suns. They're so far away that even our most powerful telescopes can barely make them look bigger than pinpricks. Yet somehow, astronomers have figured out exactly how large many of these stars are. It's like trying to measure the size of a marble from miles away, except that marble is millions of times bigger than Earth. The whole process starts with something that seems almost philosophical, the question of distance. You see, without knowing how far away something is, brightness becomes completely meaningless. Think about it this way. A flashlight held close to your face seems incredibly bright, but the sun, which is literally millions of times more powerful, looks like just another light in the sky. Stars work exactly the same way. That faint little dot you see up there might actually be pumping out more light than 1,000 of our suns. It's just so incredibly far away that barely any of that light reaches us. So the first thing astronomers need to do is figure out distance, and they do this using a technique that's surprisingly simple in concept. It's called parallax, and it works just like when you hold your finger out in front of your face and look at it with one eye, then the other. Your finger seems to jump back and forth against whatever's behind it. Astronomers do the same thing. But instead of using their two eyes, they use Earth's position on opposite sides of its orbit around the Sun. They take a picture of a star in January, then another picture in July, and measure how much the star appears to shift against the background of more distant stars. The shift is absolutely tiny. We're talking about angles smaller than the width of a human hair viewed from several miles away. But modern space telescopes are so precise they can measure these impossibly small movements. There's something almost miraculous about the fact that we can determine distances to stars that are trillions of miles away just by watching them wiggle slightly as our planet moves through space. It makes you wonder what other impossible things might actually be possible if we just look carefully enough. But parallax only works for relatively nearby stars. When you're dealing with the truly giant stars, the ones that are tens of thousands of light years away, that tiny shift becomes so small it's basically impossible to measure. So, astronomers have to get creative, and this is where things get really interesting from a detective story perspective. They turn to something called spectroscopy, which is basically spreading starlight out into a rainbow and studying all the different colors. Every chemical element absorbs and emits light at very specific wavelengths, so by looking at which colors are missing or enhanced in a star's light, astronomers can figure out what the star is made of, how hot it is, and even how bright it really is compared to how bright it appears to us. It's like being able to analyze someone's entire medical history just by looking at a photograph of them. The light carries all this information across vast distances, and we've learned how to decode it. Once you know how bright a star really is, and you can measure how bright it looks from Earth, the difference tells you exactly how far away it must be. Now here's where it gets even more fascinating. Many of the biggest stars are surrounded by clouds of dust that block visible light, so what we see with our eyes is just a fraction of what's really there. But that dust absorbs the star's light and re-emits it as infrared radiation, basically heat. So astronomers use infrared telescopes to see through the dust and get a complete picture of how much energy these giant stars are really putting out. Once they know the distance and the total energy output, they can use some fairly straightforward physics to calculate the star's size. There's a relationship called the Stefan-Boltzmann law that connects how bright something is, how big it is. Think of it this way: if you have two campfires that are giving off the same amount of total heat, but one fire is much hotter than the other, then the cooler fire must be much bigger to produce the same total energy. But astronomers don't just want to calculate sizes, they want to actually measure them when possible. And believe it or not, they found ways to do this for some stars. The technique is called interferometry, and it involves linking multiple telescopes together, so they work like one gigantic telescope. By combining the light from different locations, they can achieve resolution that's good enough to actually see the tiny disks of some nearby giant stars. The images they get aren't like regular photographs, they're more like reconstructions based on how light waves interfere with each other. But they've used this technique to actually measure stars like Betelgeuse and Antares, and what they found is pretty mind-blowing. These giant stars aren't smooth, uniform balls like we might imagine. They have enormous convection cells on their surfaces, areas of churning gas that can be bigger than our entire solar system. Some of them aren't even round, they're distorted by their own rotation or by interactions with companion stars. But measuring stellar sizes isn't straightforward, because stars don't have hard surfaces like planets do. Instead, their outer layers just gradually thin out into space. Astronomers use something called the photosphere as a reference point. That's the layer where most of the visible light comes from. But in giant stars, this layer can be thick and irregular, and different wavelengths of light can come from slightly different depths in the star's atmosphere. It's like trying to measure the size of a cloud. Where exactly do you say the cloud ends and empty air begins? This is one of those problems that makes you think about the nature of boundaries and definitions. We like to think of objects as having clear edges, but when you look closely enough, those edges often turn out to be fuzzy and ambiguous. Many giant stars make this even more complicated because they pulsate, expanding and contracting like slow heartbeats. Their brightness changes over time, and so does their size. Astronomers have to take measurements over long periods and average them out to get reliable numbers. It's a reminder that the universe isn't static. Even things as massive as stars are constantly changing. Then there's the problem of interstellar dust. Light traveling from a distant star has to pass through clouds of gas and dust that can absorb certain wavelengths and make the star appear dimmer and redder than it really is. Astronomers have to study the properties of this intervening material and correct their measurements accordingly. It's like trying to judge the true color of an object while looking at it through tinted glass. Sometimes astronomers get help from binary star systems, where a giant star has a companion orbiting around it. By studying the orbital motion, they can determine the masses of both stars, which provides additional constraints for calculating sizes and other properties. Other times they study expanding shells of gas that giant stars have puffed off into space, using the speed and size of these shells to work backwards and figure out what the star was like when it ejected the material. All of these different techniques work together, like pieces of a cosmic puzzle. Each measurement adds another constraint, another piece of information that helps narrow down the possible answers. Over time, the picture becomes clearer and more accurate. But it's an ongoing process. As new telescopes and better instruments provide more precise data, estimates of stellar sizes sometimes change significantly. A star that was once thought to be the largest known might be revised downward when a better distance measurement becomes available. Another star might turn out to be much bigger than anyone previously thought. This constant refinement is part of what makes astronomy so fascinating. We're always getting better at understanding things that seemed completely unknowable just a few decades ago. There's something profound about the fact that we can measure the size of objects so distant that their light takes thousands of years to reach us. We're essentially reaching across vast gulfs of space and time, using nothing but the information carried by photons that have been traveling since before human civilization began. In a way, every measurement of a distant star is also a measurement of our own ingenuity and persistence as a species. The way scientists narrow down their understanding of giant stars reflects something deeper about how knowledge actually works. Each new measurement doesn't just add information, it gradually eliminates possibilities, like slowly focusing a blurry photograph until the details become clear. This process takes extraordinary patience, because the light astronomers study today began its journey thousands of years ago, traveling through space while civilizations rose and fell on Earth. The stars themselves demand this kind of patience. Their outer layers drift into space in winds so gentle. They make Earth's strongest hurricanes seem violent by comparison. These stellar atmospheres stretch across distances that would swallow entire planetary systems, yet they're so tenuous that the boundary between star and space becomes almost philosophical, a gradual fading rather than a sharp edge. Distance creates the first major challenge in measuring stellar giants. When astronomers discover that a star sits 10% farther away than previously calculated, the star's estimated size must grow dramatically. It's a bit like realizing that what you thought was a nearby streetlight is actually a distant lighthouse. The implications ripple through every other measurement. Stellar distances remained frustratingly uncertain until space missions began providing more precise measurements. These improvements sometimes shrink a star's calculated size, sometimes expand it. A star once crowned as the largest known might suddenly lose its title, not because anything changed in space, but because human understanding improved down on Earth. The definition of a star's edge presents another puzzle entirely. Planets have surfaces you could theoretically stand on, clear boundaries where rock meets vacuum. Stars fade gradually into nothingness, their outer layers becoming thinner and thinner until they merge imperceptibly with interstellar space. Astronomers typically measure stellar radius at the photosphere, the layer where most visible light emerges, but this choice involves a degree of arbitrary convention. Different wavelengths of light reveal different layers of a star's atmosphere. Visible light shows one boundary, infrared radiation another, radio waves yet another. It's as if measuring a fog bank, where the answer depends entirely on which definition of edge you choose to accept. The largest stars complicate matters further by refusing to stay the same size. Many pulsate rhythmically, expanding and contracting like cosmic hearts beating over months or years. Their brightness fluctuates, their outer layers shift position, and the photosphere itself moves inward and outward in these giant stellar breaths. Measuring such a star at different times yields different results, each technically correct for that moment. Dust adds another layer of uncertainty to these cosmic measurements. Giant stars shed material constantly, surrounding themselves with thick envelopes of gas and particles. This debris absorbs visible light, making stars appear dimmer, and sometimes changing their apparent size entirely. Infrared observations can peer through this dusty veil more effectively, but interpreting these longer wavelengths requires sophisticated models of how dust interacts with starlight. The universe keeps surprising astronomers with new discoveries. Infrared surveys regularly reveal previously unknown giants hiding behind cosmic dust clouds, some potentially larger than any known star. Vast regions of our galaxy remain unexplored in detail, suggesting that even more massive stars might exist in areas too distant or obscured for current technology to study properly. Theoretical models add their own source of uncertainty to stellar measurements. When astronomers estimate a star's properties, they rely on complex mathematical descriptions of stellar atmospheres, equations that describe how temperature, pressure, and radiation behave in stellar outer layers. These models rest on well-tested physics, but they still require assumptions and approximations about conditions no laboratory can recreate. As theoretical understanding improves, stellar size estimates change accordingly. A star once calculated as enormous might shrink when analyzed with better models, while another might grow larger under more sophisticated analysis. This revision process exemplifies science at its most honest, acknowledging that knowledge advances through continuous refinement rather than sudden revelation. The concept of largest becomes surprisingly complex when applied to stars. One star might claim the greatest radius, another the highest mass, a third the most luminosity. These represent different kinds of largeness, much like comparing the tallest building to the heaviest ship to the most populated city. Each measurement captures a different aspect of cosmic enormity. Stars also change over time, adding a temporal dimension to any discussion of stellar records. The largest star today might explode next week, astronomically speaking, while a currently smaller star might expand dramatically in its future evolution. Astronomers essentially photograph stars at single moments in lives that span millions of years, creating snapshots of an ever-changing cosmic population. This temporal uncertainty adds philosophical depth to astronomical records. They represent observations of a dynamic universe caught in particular moments, not permanent achievements etched in stone. The largest star of today differs from the largest star of 1,000,000 years ago, and both will likely differ from the largest star of the distant future. The universe reveals its secrets through this gradual accumulation of understanding rather than dramatic revelations. Each measurement refines the picture slightly. Each observation narrows the range of possibilities. There's something profoundly patient about this process, matching the vast timescales over which stars themselves evolve. These cosmic giants live brief lives compared to smaller stars, burning through their nuclear fuel with reckless intensity. Their enormous size comes at the cost of stability and longevity, making them cosmic fireworks that blaze brilliantly before fading. The largest stars represent extremes of stellar evolution, pushing the boundaries of what gravity and nuclear fusion can sustain. All this knowledge emerges from analyzing faint streams of photons, particles of light that have traveled unimaginable distances to reach Earth's telescopes. The information content of starlight seems impossibly rich, encoding details about temperature, composition, motion, and structure across the light years. That such detailed understanding can emerge from such tenuous evidence speaks to both the ingenuity of human investigation and the fundamental interconnectedness of physical processes throughout the universe. Binary star systems present fascinating puzzles for astronomers. Sometimes what appears to be a single, massive star turns out to be two stars orbiting each other so closely that their light blends together. When this discovery happens, everything needs to be recalculated. The brightness measurements, the size estimates, even the basic understanding of what you're looking at, all of it changes. It's like realizing that what you thought was one candle in the distance was actually two candles sitting side by side. Dust clouds can play similar tricks on our observations. A star might seem enormous because thick clouds of gas and debris surround it, making it appear larger and dimmer than it really is. As our telescopes get better, these illusions become clearer. What once seemed like a record-breaking giant might turn out to be a more ordinary star wearing a cosmic disguise. This uncertainty isn't a flaw in astronomy, it's actually one of its strengths. Scientists don't pretend to have perfect knowledge, they embrace the unknown. Error bars appear on every measurement, ranges get reported instead of exact numbers, and conclusions come with careful caveats. This honest approach to uncertainty allows knowledge to grow steadily over time. Each new observation builds on previous work without claiming to be the final word. There's something deeply human about this process, the way we slowly piece together understanding from incomplete information. The largest stars challenge our imagination in ways that go beyond simple measurements. These stellar giants have atmospheres that stretch across distances comparable to planetary orbits. Their outer layers are so diffuse, they gradually fade into the emptiness of space. There's no sharp edge, no clear boundary where the star ends and space begins. Instead, there's a gradual transition from the dense, blazing interior to the near vacuum of interstellar space. If you could somehow travel through the outer layers of a giant star, the experience would be surprisingly gradual. The gas would slowly grow denser as you moved inward. The light around you would strengthen bit by bit, and the temperature would rise in small increments. This gentle progression reflects the fundamental nature of these cosmic structures. They're not solid objects with defined surfaces, but rather enormous balls of gas held together by their own gravity. The interior of a giant star reveals a complex, layered structure that operates like a vast nuclear furnace. At the very center, temperatures reach tens of millions of degrees. The pressure there is almost beyond comprehension, created by the immense weight of all the layers above pressing inward. In this extreme environment, atomic nuclei move so rapidly that they overcome their natural repulsion and fuse together, releasing tremendous amounts of energy. This fusion process is what keeps stars shining and prevents them from collapsing under their own weight. In smaller stars like our Sun, hydrogen fusion in the core can continue steadily for billions of years. But giant stars operate under different rules. Many have already exhausted the hydrogen in their cores, forcing them to burn heavier elements in a complex sequence. The core contracts and heats up, and fusion begins occurring in shells surrounding the center rather than just at the core itself. This creates a structure sometimes compared to an onion, with different types of fusion happening at different depths. Near the center, heavier elements fuse together, while farther out, lighter elements continue burning in distinct shells. Each layer produces energy that must somehow travel outward through the star. The journey of this energy depends on the conditions in each region. Sometimes it moves as radiation, with photons gradually working their way outward, being absorbed and re-emitted countless times. In other regions, especially the outer layers of giant stars, energy travels through convection, the slow rising and sinking of hot gas. The scale of convection in these stellar giants is truly spectacular. Instead of the small-scale bubbling you might see in boiling water, giant stars can have convection cells so large that only a few cover the entire surface. Imagine currents of gas rising and falling across distances greater than Earth's orbit, moving slowly and steadily over months or years. These massive convection patterns shape the brightness of the star, causing subtle variations in light that astronomers can detect from thousands of light years away. And question of depth from thousands of light years away. The process reminds us that even the most distant objects in the universe are dynamic, constantly changing systems rather than static points of light. As energy works its way outward, the temperature gradually decreases. By the time it reaches the outer layers, the gas has cooled to only a few thousand degrees, which explains why these stars appear red or orange rather than white or blue. Even at these relatively cooler temperatures, the environment would be utterly hostile by any earthly standard. The gas still glows with its own light, still moves in vast currents, still participates in a system powered by nuclear reactions deep within. Radiation pressure plays a crucial role in the most massive stars. Light itself carries momentum, and when photons streaming outward from the core interact with the gas in the star, they exert a real physical force. In the largest stars, this radiation pressure becomes so strong that it nearly balances gravity on its own. This creates a delicate equilibrium that makes giant stars inherently unstable. A small change in temperature or energy production can shift the balance, causing the outer layers to expand or contract. These changes often produce pulsations, gentle breathing motions, where the star's radius increases and decreases in slow rhythmic patterns. Some giant stars experience more irregular variations, driven by the complex interplay between convection, radiation, and a gradual loss of mass into space. Mass loss is a constant process for many giant stars. The outer layers are only loosely bound by gravity, and stellar winds carry material outward into space at a steady rate. These winds might seem gentle compared to the violent explosions that eventually end a star's life, but their persistence makes them significant. Over thousands or tens of thousands of years, they can remove a substantial fraction of the star's total mass. This lost material doesn't simply vanish into nothingness. It drifts outward, forming shells and clouds of gas and dust that surround the star like ghostly reminders of its former self. Sometimes these clouds glow in infrared light, warmed by radiation from the star that created them. In this sense, every giant star exists surrounded by traces of its own history, layers of material it once contained now slowly expanding into the cosmos. The most dramatic changes happen deep in the core, where the star's nuclear engine operates under increasingly extreme conditions. As heavier elements accumulate, the core becomes denser and hotter with each stage of fusion. But there's a cruel irony at work. Each new type of fusion produces less energy than the previous stage, and the timescales become dramatically shorter. Hydrogen burning might last for millions of years, helium burning for hundreds of thousands, carbon burning for perhaps hundreds of years, and the final stages might last only days or hours. This accelerating sequence resembles a clock ticking faster and faster, though from the outside, the star might appear calm and steady. The contrast between the star's serene external appearance and the increasingly frantic nuclear processes within reflects one of the universe's most profound mysteries: the way complex systems can maintain apparent stability even as they approach fundamental transitions. The largest stars operate under physical principles that smaller stars never encounter. While a star like our Sun relies primarily on thermal pressure from the motion of hot particles, massive stellar giants experience additional forces including radiation pressure and quantum mechanical effects that arise under extreme conditions. These exotic physics regimes remind us that the universe contains environments so extreme they stretch the boundaries of our everyday understanding of matter and energy. Within the heart of massive stars, a profound tension plays out across scales that stretch our imagination. Quantum mechanics, the science that governs the smallest particles, somehow dictates the fate of object solar systems. It's a reminder that the universe operates on principles that connect the tiniest and the most colossal in ways we're still learning to appreciate. These stellar giants produce something almost ghostly, particles called neutrinos that barely interact with anything around them. They're nearly massless, almost like whispers of matter, yet they pour out from stellar cores in unimaginable numbers. In the final moments of a massive star's existence, these elusive particles become crucial messengers of doom, carrying away energy so rapidly they help trigger the very collapse that births a supernova. What strikes you about this process is how hidden it all remains. We can't peer directly into a star's interior, can't watch these cosmic dramas unfold in real time. Instead, astronomers piece together the story from fragments of light that escape the surface, from mathematical models that describe how matter behaves under extreme conditions. It's detective work on a cosmic scale, reconstructing the biography of an object larger than our entire planetary neighborhood, from nothing more than faint points of light scattered across the night sky. There's something deeply satisfying about discovering that the same physical laws governing a campfire or a laboratory experiment also rule inside these stellar monsters. Gravity pulls inward with relentless determination. Pressure pushes outward with equal stubbornness. Hot regions always try to share their energy with cooler neighbors. Nuclear fusion follows the same rules whether it happens in a research facility or in a furnace millions of times hotter than anything on Earth. The interior of a giant star resembles a vast interconnected machine, where every component affects every other component. Conditions in the core determine how much energy flows outward, which shapes the behavior of the outer layers, which influences how the star sheds mass into space. It's a delicate dance that can continue for millions of years, but it cannot continue forever. Eventually, the core reaches a point where fusion can no longer generate enough energy to hold up against gravity's inexorable pull. Perhaps the most mind-bending aspect of stellar giants involves the journey that light takes from their cores to their surfaces. Photons created deep inside these stars don't travel in straight lines toward space. Instead, they embark on what scientists call a random walk, getting absorbed and re-emitted countless times as they slowly work their way outward through incredibly dense layers of stellar material. This process can take an almost incomprehensible amount of time. For stars like our Sun, energy produced in the core might take tens of thousands of years to reach the surface. In giant stars, with their extended atmospheres and complex internal structure, the journey can last even longer in some regions. The light leaving a giant star's surface today might have begun its journey before human beings developed written language. When we consider the sheer size of these stellar behemoths, numbers alone fail to capture the reality. Some giant stars have radii hundreds of times larger than our Sun, occasionally exceeding 1,000 times the solar radius. They can span distances greater than the orbit of Jupiter, sometimes reaching nearly to Saturn's path around our Sun. To truly grasp these dimensions, think about light itself. Light travels at roughly 300,000 kilometers per second, fast enough to circle Earth more than 7 times in a single second. In our everyday experience, light seems instantaneous. Rooms illuminate the moment we flip a switch. Sunrise appears to happen all at once. But even light, the fastest phenomenon in the universe, takes measurable time to cross the largest known stars. Hours can pass as a photon travels from one edge of a supergiant to the other edge. Imagine hovering near such a star's surface, looking toward the opposite horizon. That distant edge would be so far away that light leaving that region would take hours to reach your location. This creates a strange situation where different parts of a single star exist in slightly different moments of time from the perspective of light traveling between them. Information cannot instantly spread throughout the stellar structure. Pressure waves, shock fronts from pulsations, convection currents in the outer layers, all these processes unfold over timescales that reflect the immense distances involved. The largest stars exhibit convection patterns that can take months or years to complete a single cycle. Imagine atmospheric currents so vast that a complete circulation requires more time than most earthly seasons. These slow, majestic flows help transport energy and material throughout the star's extended atmosphere, contributing to the complex processes that eventually lead to mass loss and stellar evolution. Once light finally escapes from a giant star's surface, its journey through space begins. Many of the giant stars visible to us lie thousands of light years away. A light year represents the distance light travels in one full year, approximately 9.46 trillion kilometers. Even traveling at the ultimate cosmic speed limit, light from distant giants requires thousands of years to reach Earth. This means every giant star we observe shows us an image from the distant past. The star, as it exists in this exact moment, differs slightly from what we see. Because its current light hasn't had time to reach us yet, we're perpetual time travelers, gazing backward through cosmic history every time we look up at the night sky. There's something profoundly peaceful about this realization. Each point of light carries a message across both space and time, connecting us to stellar events that occurred long before our civilization began. The photons entering our eyes tonight began their journeys when ancient empires rose and fell, when ice ages came and went, when our planet looked completely different than it does today. This temporal displacement affects how we understand stellar processes. Changes occurring inside a giant star cannot instantly influence its entire structure. The star exists as a complex system where different regions operate on different timescales, where cause and effect unfold gradually across distances that would swallow multiple planetary orbits. When light begins its journey from the core of a giant star, it faces a path unlike anything we experience in our daily lives. The photons don't simply zip straight to the surface, the way light might travel across a room. Instead, they wander, bounce, and drift through layers of gas, so thick and dense that the journey becomes an epic of cosmic proportions. In smaller stars like our Sun, this process takes thousands of years, but in the truly massive stars, the ones that dwarf our solar system, light can spend tens of thousands of years just trying to reach the surface. Think about that for a moment. A single photon of light, born in the nuclear fires at the star's heart, might begin its outward journey when human civilization was just learning to farm, and only now be emerging into space. This creates something fascinating, a kind of cosmic delay system. The energy we see streaming from these stellar giants was actually created long before recorded history began. The star's surface glows with ancient light, while deep in the core, completely different nuclear reactions are happening right now. It's as if the star exists in multiple time periods simultaneously. The sheer distance involved explains why these stars seem to pulse and flicker in ways that smaller stars don't. When something changes deep inside the star, perhaps a shift in the nuclear burning rate, or a movement in the convective currents, it takes an enormous amount of time for that change to work its way outward. The star's surface might be responding to events that happened centuries ago. Gas in the outer regions of these massive stars moves at what seems like incredible speeds, tens of kilometers per second. By earthly standards, that's remarkably fast. But when you consider the size of these stars, those high-speed gas currents are actually moving quite gently. It's like watching a mountain-sized balloon inflate, the surface expanding quickly in absolute terms, but slowly relative to its enormous scale. Material drifting through the outer layers of a hypergiant might take months or even years to travel from one side to the other. Imagine a single atom of hydrogen caught in one of these stellar winds, beginning a journey across the star's diameter. That atom would be traveling for longer than some human lifetimes, just to cross from one edge to the other. This creates a strange relationship with time itself. We live our lives in decades. Our civilizations rise and fall over centuries. But these stellar processes unfold over timescales that make human history seem like a brief flicker. The most dramatic changes in a giant star's life, the phases that astronomers consider rapid, still take longer than all of recorded human experience. There's something almost meditative about contemplating these vast, slow processes. The universe operates on its own schedule, unhurried by our human sense of urgency. Changes that would transform our entire world happen gradually, steadily, following the patient laws of physics across millions of years. When astronomers measure these distant giants, they're essentially looking backward through time, seeing light that left the star's surface long ago, carrying information about nuclear processes that happened even longer ago than that. It's a kind of cosmic archaeology, reconstructing the history of stellar events from the ancient photons that finally reach our telescopes. The largest of these stars can have diameters that stretch beyond the orbit of Jupiter. If you could somehow fly a commercial aircraft across one of these stellar giants, traveling at normal airplane speeds, the journey would take years. Even a spacecraft moving many times faster would need months to complete the crossing. These comparisons help us grasp the scale, but they also reveal how limited our everyday experience really is when it comes to understanding cosmic distances. Despite these immense scales, astronomers can study these stars with remarkable precision. They analyze the spectrum of light, the way it flickers and changes, the subtle shifts that reveal temperature, composition, and motion. It's remarkable that from such vast distances, we can determine what's happening inside these stellar giants, reconstruct their internal processes, and predict their future evolution. Now, imagine for a moment what would happen if one of these massive stars somehow took the place of our Sun, not suddenly, not catastrophically, but gradually, as if the universe was slowly adjusting the scale of our solar system. Picture the Sun growing larger and cooler, its surface expanding outward, first engulfing Mercury's orbit, then Venus, then reaching toward Earth. The sky would change in ways that are difficult to imagine. Instead of a bright, compact disk, our star would become an enormous glowing sphere that fills a huge portion of the heavens. The light would be different too, redder and softer, more diffuse. There would be no sharp sunrise or sunset, no clear transition between day and night. Instead, the sky would glow continuously with a gentle reddish luminescence. From Earth's surface, if we could somehow survive such a transformation, we would see vast currents of glowing gas moving slowly across the star's surface. These convection cells would be larger than entire planets, rising and falling over weeks or months. Driven by the enormous energy generated in the star's core, the inner planets would find themselves immersed in the star's outer atmosphere, no longer orbiting through empty space, but moving through thin but intensely hot gas. Mercury and Venus would be deep within these stellar layers, while Earth might hover near the edge, experiencing conditions unlike anything in our current solar system. The outer planets, Jupiter and Saturn, might continue their orbits beyond the star's surface, but their environment would be transformed. The sky from Jupiter would be dominated by an enormous red disk, far larger than our Sun appears from Earth. The radiation would be intense, the stellar wind much stronger than what we experience today. What's particularly interesting is that this giant replacement star might not actually be much more massive than our current Sun. Many red supergiants are only 10 or 20 times the Sun's mass, despite being hundreds of times larger. Size and mass are different things in stellar physics. The star achieves its enormous diameter not by containing more material, but by expanding its existing material across a much larger volume. This expansion happens because the star's outer layers are only weakly held by gravity. The intense radiation pressure from the core pushes outward, while gravity pulls inward. And in these massive stars, the balance point creates a surface that extends far beyond what we might expect. Gas escapes continuously from these outer layers, creating a stellar wind that carries material into interstellar space. Over time, this escaped material forms glowing shells around the star, illuminated by the intense radiation from within. These nebulae become part of the star's extended atmosphere, visible as faint, colorful clouds that can stretch across light years of space. The lifespan of such a massive star would be dramatically different from our Sun's expected lifetime. While our Sun will burn steadily for billions of years, a red supergiant lives fast and dies young. These stellar giants might exist in their expanded state for only a few 100,000 years before reaching the final stages of their evolution. This brief lifetime means that if such a star replaced our Sun, the entire configuration would be temporary on astronomical timescales. The star would be racing toward a dramatic end, building heavier and heavier elements in its core, approaching the moment when nuclear fusion can no longer support the star's enormous mass. From a safe distance, far beyond the star's outer layers, an observer might watch these slow changes unfold over centuries. The star's brightness might vary slightly as internal processes shift and change. Great shells of gas might drift outward, forming expanding rings of glowing material. The whole system would be in a state of constant, gentle transformation. There's something profound about imagining our familiar solar system on this new scale. Distances that seem vast in our current configuration would become small compared to the star's diameter. The orbit of Mars, which takes nearly 2 years to complete, would lie entirely within the star's atmosphere. Jupiter's orbit, which we think of as representing the outer edge of the inner solar system, might barely extend beyond the star's visible surface. This change in perspective reminds us that scale is always relative. What seems large in one context becomes small in another. Our entire conception of space and distance depends on the frame of reference we choose. The giant star doesn't just change the physical structure of the solar system, it transforms our entire sense of proportion and scale. Even in this imagined scenario, the fundamental processes of stellar physics continue to operate. Nuclear fusion in the core converts hydrogen to heavier elements. Radiation pressure pushes outward against gravity's inward pull, Convection currents transport energy from the interior to the surface. The same physical laws govern both our modest sun and these stellar giants, but the scale of their operation creates entirely different outcomes. The stellar wind from such a massive star would be far more intense than anything our sun produces, carrying away significant amounts of material and enriching the surrounding interstellar medium with heavy elements forged in the star's core. This material becomes part of the cosmic recycling system, eventually incorporated into new stars and planets elsewhere in the galaxy. In contemplating these massive stars and their brief, dramatic lives, we encounter one of the universe's most fundamental patterns, the cycle of stellar birth, evolution, and death that drives the chemical evolution of galaxies. These giants, despite their short lives, play a crucial role in creating the elements necessary for planets and life itself. When we think about size in the universe, our everyday experience can mislead us. In our daily lives, bigger usually means longer lasting. A thick candle outlasts a thin one. A large fuel tank powers a car farther than a small one. But the cosmos operates by different rules that seem to flip our intuition upside down. The most massive stars in the universe, these giants that dwarf our sun by hundreds of times, live the shortest lives. It's a cosmic irony that reveals something profound about the nature of existence itself. Scale and duration don't always go hand in hand, whether we're talking about stars or perhaps other aspects of life. Nuclear fusion powers every star, this remarkable process where hydrogen atoms merge deep in the core, creating helium and releasing tremendous energy. The energy pushes outward while gravity pulls inward, creating a delicate balance that keeps a star stable for millions or billions of years. But when a star is truly massive, this balance becomes more like a high wire act. Massive stars have stronger gravity pulling everything inward. To fight against this crushing force, the core must work much harder, fusing hydrogen at a dramatically faster rate. It's not a simple relationship either. A star twice as massive as our sun doesn't just burn twice as fast, it might burn several times faster. A star 10 times more massive can shine tens of thousands of times brighter. Think of it like comparing a gentle campfire to an industrial furnace. The furnace has more fuel, yes, but it consumes that fuel at such a rapid pace that it burns out much sooner than the steady campfire. The bigger the star, the more frantically it burns through its nuclear fuel. Our sun will spend about 10 billion years steadily fusing hydrogen in its core. But a star 20 times more massive might race through this same phase in just a few million years. In cosmic terms, that's like living for a single day instead of a full human lifetime. After the hydrogen runs out, these massive stars begin a kind of accelerating countdown. The core contracts and heats up, starting new types of fusion. Helium fuses into carbon and oxygen, then heavier and heavier elements form in successive stages. Each stage happens faster than the last, like a runaway train picking up speed. Hydrogen burning might last millions of years, but helium burning lasts only hundreds of thousands. Carbon burning might take just a few hundred years, and the final stages can unfold in mere days or hours. The star seems to race toward its own destruction, consuming its remaining fuel in increasingly desperate bursts. There's something almost tragic about this cosmic sprint. These stellar giants lose enormous amounts of material through powerful stellar winds. Radiation pressure pushes gas away from the star, and the outer layers, already barely held by gravity, drift into space like cosmic dust. Over time, a massive star can shed a significant portion of its mass this way. The cores of these giants burn hotter and denser than smaller stars, and temperature makes all the difference in nuclear fusion. Even a small increase in core temperature can dramatically boost the fusion rate, creating a kind of feedback loop. Stronger gravity compresses the core, raising the temperature, which increases fusion, which produces more energy, but also burns through fuel faster. In the most massive stars, radiation pressure becomes a major force pushing outward against gravity. Photons streaming from the core exert real pressure on the gas above, helping to support the star's outer layers, but this creates a delicate, unstable situation. Small changes can cause the outer layers to expand or contract unpredictably. These giants don't mix their fuel efficiently either. While convection moves material around in some regions, other parts remain layered, with heavier elements sinking toward the core and lighter ones staying in the outer layers. This means not all the star's hydrogen can participate in fusion at once, further limiting the effective fuel supply. Despite their brief lives, massive stars have an enormous impact on everything around them. Their intense radiation ionizes nearby gas, creating those beautiful glowing nebulae we see in space photographs. Their stellar winds carve vast bubbles in the space between stars. And when they finally explode as supernovae, they scatter heavy elements across incredible distances. Those elements, carbon, oxygen, silicon, iron, and many others, become part of new stars, new planets, and eventually new life. In this sense, the brief, brilliant existence of massive stars plays a crucial role in cosmic evolution. They live fast and die young, but their death gives birth to the building blocks of complexity. There's something quietly striking about this contrast between size and lifespan. A giant star might be thousands of times larger than our Sun, yet it lives only a tiny fraction as long. It reminds us that in nature, intensity often shortens life rather than prolonging it. Even observing these changes requires a cosmic perspective. A few million years seems immense compared to human history, but it's brief compared to the billions of years that smaller stars endure. Astronomers sometimes describe massive stars as living fast and dying young, though of course stars don't experience time or make choices. They simply follow the laws of physics, their evolution determined by mass, composition, and the nuclear processes in their cores. As these giants age, their internal structure becomes increasingly complex. Heavier elements accumulate in the core, and fusion becomes less efficient at producing energy. Each successive stage releases less energy per reaction, forcing the core to contract further to reach the temperatures needed for fusion. Eventually, the core reaches a stage where fusion can no longer provide enough energy to support the star. Iron, the final product of fusion in massive stars, actually absorbs energy when atoms try to fuse, making further fusion impossible. When the core becomes mostly iron, the balance between gravity and pressure can no longer be maintained. This is where the long, quiet approach to catastrophe begins. From the outside, the star may still appear steady, glowing with familiar light, its outer layers drifting slowly outward in gentle stellar winds. Nothing suggests urgency. Nothing hints at how close the end may be in cosmic terms. But inside, the balance that sustained the star for millions of years is shifting. The core becomes denser and denser, electrons forced closer together, pressure rising to extraordinary levels. Eventually, a point is reached where the core can no longer support itself, and collapse becomes inevitable. When that collapse begins, it happens with stunning speed. The core, perhaps as large as Earth, can collapse in a fraction of a second. Gravity pulls matter inward so rapidly that atoms are crushed together, protons and electrons combining to form neutrons. The core becomes incredibly dense, either a neutron star or, if massive enough, a black hole. This sudden collapse sends a shockwave outward through the star. The shock, combined with a flood of particles released during the collapse, blows the outer layers into space in a supernova explosion. For a brief time, the star can outshine an entire galaxy, releasing more energy in weeks than our Sun will emit in its entire lifetime. What makes this ending remarkable isn't just the explosion itself, but the long, quiet build-up that precedes it. For hundreds of thousands of years, the star may exist in growing instability, its outer layers pulsating, its mass slowly decreasing through stellar winds, its core moving steadily toward the point where fusion can no longer sustain it. There's something quietly fascinating about observing a star nearing the end of its life. The light we see left the star years or centuries ago, yet within that light are clues about processes unfolding deep inside, processes that will eventually lead to one of the most powerful events in the universe. It serves as a reminder that even the most immense and seemingly eternal objects are subject to change, part of the great cosmic cycle of birth, life, and transformation that continues throughout the galaxy. When we look up at the night sky, we're witnessing a cosmic recycling program that's been running for billions of years. Every atom in your body, except for hydrogen, was forged inside a star that lived, died, and exploded long before our sun even existed. The calcium strengthening your bones right now, the iron carrying oxygen through your bloodstream, the oxygen you're breathing, all of it came from the heart of a giant star that met its end in one of the universe's most spectacular events. These stellar giants don't simply burn out quietly like a candle. After millions of years of steady burning, their final moments arrive with shocking suddenness. Picture a long, peaceful evening that ends with a brilliant flash of lightning. That's essentially what happens when a massive star finally runs out of fuel. For eons it burns, swells, and slowly sheds material into space, but the actual collapse and explosion happen in mere seconds. The physics behind this process reveal something fascinating about the nature of existence itself. Throughout a star's life, two fundamental forces wage a constant battle. Nuclear fusion in the core pushes outward, while gravity relentlessly pulls inward. For millions of years, fusion wins this cosmic tug-of-war, but gravity is patient. It waits, persistent and unchanging, until the moment when the star can no longer resist. When that moment arrives, the core collapses with such violence that matter gets compressed to densities we can barely comprehend. A teaspoon of this material would weigh billions of tons on Earth. The outer layers, suddenly losing their support, fall inward briefly before rebounding in a shock wave that tears the entire star apart. The energy released in those few seconds exceeds what our sun will produce during its entire 10 billion year lifetime. Most of this energy escapes as neutrinos, ghostly particles that pass through matter, almost without interacting. Right now, trillions of these particles from distant stellar explosions are streaming through your body, through the Earth, through everything, as if we weren't even there. Only a small fraction of the explosion's energy drives the visible fireworks we call a supernova. Ancient astronomers sometimes recorded these events as new stars appearing where none had been visible before. They had no way of knowing they were witnessing the death throes of stellar giants located thousands of light years away. The explosion makes the dying star so luminous that it can outshine an entire galaxy of billions of other stars, at least for a few weeks or months. What remains after the outer layers have been blasted into space is a vast expanding cloud of gas called a supernova remnant. These cosmic sculptures can persist for thousands of years, slowly spreading their stellar debris into the surrounding space. The Crab Nebula, visible through telescopes today, is the remnant of a supernova that Chinese astronomers observed in the year 1054. They described a bright new star that was visible even during daylight for weeks. This process represents one of the universe's most important recycling mechanisms. The early cosmos contained almost nothing but hydrogen and helium, all the heavier elements, the building blocks of rocky planets and living organisms, had to be manufactured inside stars and distributed by stellar explosions. Without supernovas, the universe would be a much simpler and arguably lonelier place. The expanding shockwaves from these explosions don't just scatter elements, they actively trigger the formation of new stars. When the blast wave encounters nearby gas clouds, it compresses them, causing regions to collapse under their own gravity. In this way, stellar death becomes stellar birth, completing a cycle that has been repeating for billions of years. Multiple supernovas occurring in the same region can create enormous bubbles in space, structures called superbubbles that span hundreds of light years. These cosmic cavities affect how gas moves through the galaxy, influencing where and how new stars will form. Giant stars act as engines of galactic evolution, reshaping their neighborhoods both during their lives and in their deaths. Not every stellar core that survives a supernova explosion faces the same fate. If the remaining core isn't too massive, it becomes a neutron star, an object so dense that more mass than our entire sun gets compressed into a sphere only about 20 kilometers across. Some of these neutron stars spin rapidly, emitting beams of radiation that sweep through space like lighthouse beams. When these beams cross Earth, we detect regular pulses of radio waves, cosmic heartbeats from the remnants of dead giants. If the core is even more massive, gravity overwhelms all other forces completely. The core collapses into a black hole, an object so dense that not even light can escape its gravitational pull. These stellar mass black holes represent the ultimate victory of gravity over all other forces in nature. Under the most extreme conditions, certain very massive stars undergo what astronomers call pair instability supernovas. These explosions are so energetic that they completely obliterate the star, leaving absolutely nothing behind except an expanding cloud of debris. Even by supernova standards, these events are extraordinary, demonstrating just how powerful the deaths of the most massive stars can be. The rarity of these events adds to their mystique. In our galaxy, supernovas occur roughly once every century, though many go unnoticed because they're hidden by dust or happen on the far side of the galaxy. Most giant stars are located thousands of light years from Earth, far enough that their explosions are spectacular to observe but pose no threat to us. However, scientists have discovered traces of radioactive isotopes in ocean sediments that likely came from supernovas that occurred millions of years ago, relatively close in astronomical terms. These ancient signatures remind us that the processes shaping our galaxy aren't entirely disconnected from our planet's history. There's something quietly profound about contemplating these stellar life cycles. Giant stars live fast and die young, but their influence extends far beyond their brief existence. They're cosmic alchemists, transforming simple elements into the complex chemistry that makes planets and life possible. Their deaths seed the galaxy with the raw materials for future generations of stars, planets, and perhaps living worlds. Even these extraordinary giants face limits set by the laws of physics. There are boundaries on how massive or how large a star can become before instability and mass loss prevent further growth. In a universe governed by physical laws, even the most extreme objects must eventually yield to forces beyond their control. The story of giant stars and their explosive deaths connects us to the broader narrative of cosmic evolution. We are, quite literally, made of star stuff, participants in a story that began with the first stellar explosions billions of years ago and continues today as new stars form from the enriched debris of their predecessors. Each supernova represents both an ending and a beginning, a cosmic punctuation mark in the ongoing sentence of galactic evolution. When astronomers peer into the depths of space and discover stars so enormous they could contain entire planetary orbits, a fascinating question emerges naturally from our curious minds. Could there be even more colossal giants lurking out there, waiting to be found? The universe has this remarkable way of constantly surprising us, yet it also follows certain unbreakable rules that keep everything from spiraling into complete chaos. The birth of a star begins with something almost poetic in its simplicity. Gravity slowly pulls together clouds of gas and dust, like an invisible hand gathering cosmic ingredients. As more and more material collects in one place, you might think a star could just keep growing forever, as long as there's enough fuel floating around. But the universe has other plans. Something remarkable happens when a forming star reaches a certain size. The sheer brightness it produces creates what scientists call radiation pressure. Think of it as light itself becoming a physical force, pushing outward against anything trying to fall into the star. It's almost as if the star develops a protective bubble around itself, rejecting the very material it needs to grow larger. This cosmic tug-of-war between gravity pulling inward and light pushing outward creates a natural speed limit for stellar growth. Most stars can't exceed about 150 to 200 times the mass of our Sun. There might be rare exceptions hiding in unusual corners of the galaxy. But beyond this range, forming a stable star becomes nearly impossible. It's like trying to build a house of cards in a windstorm. The bigger it gets, the more likely it is to collapse under its own contradictions. Here's where things get interesting though. Mass and size aren't the same thing at all. Some of the most enormous stars we know aren't necessarily the heaviest. Instead, they're aging giants that have puffed up their outer layers like cosmic balloons. These elderly stars stretch their atmospheres across mind-boggling distances, creating some of the largest objects in the known universe. But even this expansion has limits. As a star grows larger, its outer edges become more and more weakly connected to the center. Gravity weakens with distance, following mathematical laws that can't be negotiated with. The gas at the very edge of these expanded stars becomes so thin, so loosely bound, that stellar winds can carry it away into space. If a star tried to grow too large, it would simply lose its outer layers faster than it could maintain them. Temperature plays a crucial role in this cosmic balancing act. For a star to become truly gigantic, its surface needs to be relatively cool, allowing its energy to spread over that vast area. But if the surface gets too cool, something unexpected happens. The outer layers become unstable, forming dust particles and complex molecules that actually help material escape from the star. It's like the star accidentally creates the tools for its own shrinkage. The internal workings of these massive stars present their own challenges. Energy produced in the core has to travel outward through all those layers of stellar material. If the star becomes too extended, this energy transport system starts to break down. Convection currents and radiation can't move energy efficiently enough to keep everything stable. The star develops hiccups, pulsations, and eruptions that throw material into space. All these factors work together like a committee of cosmic referees, setting practical limits on how large a star can become. Yet the universe still finds ways to surprise us, as it always does. Astronomers keep discovering new giant stars, some of which challenge what we thought we knew about stellar limits. Infrared telescopes have revealed stars hiding behind thick curtains of dust, invisible to our eyes, but blazing with incredible brightness. Better distance measurements have forced scientists to revise their estimates of how large some known stars really are. The exact location of these cosmic speed limits remains an active area of research, with new discoveries constantly refining our understanding. One fascinating possibility involves stellar collisions in dense star clusters. When stars live in crowded neighborhoods, close encounters become inevitable. Occasionally, two massive stars might actually collide and merge, creating a single, temporarily larger star. These merger products can briefly exceed the normal limits for single star formation, though they're usually unstable and lose mass rapidly. They offer glimpses of how nature occasionally pushes beyond typical boundaries. The early universe might have produced even more extreme examples. The very first generation of stars formed from primordial gas containing almost no heavy elements. Without these heavier elements, some of these ancient stars may have grown to hundreds of times our sun's mass or even more. These cosmic pioneers lived fast and died young, exploding billions of years ago and seeding space with the elements needed for planets and life. Even these primordial giants faced fundamental limits, though. Gravity, radiation pressure, and mass loss remain universal forces that no star can completely ignore. They're like cosmic laws of physics that apply everywhere, everywhen. Perhaps the most profound way to think about stellar size limits involves the concept of stability itself. Every star represents a delicate balance between forces trying to crush it inward and forces trying to blow it apart. Push that balance too far in either direction, and the star must change. It might contract, expand, shed layers, or collapse entirely. The largest stars we observe today already exist near the edge of this stability. Their outer atmospheres churn turbulently, their brightness flickers and varies, and they constantly lose material to space. In a very real sense, they're living on borrowed time, existing in states that cannot last long by cosmic standards. While slightly larger stars than current record holders probably exist somewhere out there, waiting to be discovered, there's no evidence for stars vastly larger than those we already know. The fundamental limits imposed by physics seem to prevent stars from growing indefinitely, creating a cosmic ceiling that even the universe's most extreme objects cannot breach. This raises profound questions about the nature of limits themselves. In a universe that seems infinite in scope, why do individual objects face such definite boundaries? Perhaps these limits serve a deeper purpose, preventing the universe from creating objects so extreme they would destabilize everything around them. Or maybe they simply reflect the mathematical relationships that govern how matter and energy interact on the largest scales. The universe operates according to certain fundamental rules, and these rules create boundaries that determine what can exist and what cannot. There's something deeply comforting about this concept. Even though space stretches beyond our imagination, there are still limits that govern how large a star can grow, how hot it can burn, how long it can survive. When we think about the biggest stars in the cosmos, we're really thinking about the outer edges of what's possible. These stellar giants push against the very limits of physics. Their immense size doesn't feel restrictive, though. It feels liberating, showing us just how vast the range of possibilities truly is in nature. The thing about record holders in astronomy is that they're always temporary. New telescopes reveal new objects, better measurements refine our understanding, and occasionally something completely unexpected shows up in our data. The universe keeps surprising us, reminding us that there's always more to discover, always another layer of complexity waiting to be uncovered. But the real story isn't about which particular star currently holds the title of largest. The fascinating part is understanding the processes that allow stars to grow so enormous in the first place, and then figuring out what forces eventually say, "No, this is as big as you can get." Giant stars don't exist in isolation, floating alone in empty space like distant light bulbs. They're constantly interacting with their surroundings, changing everything around them in ways that are both subtle and dramatic. Their influence reaches far beyond their visible surfaces, extending into the gas and dust that fills the space between stars. Light itself becomes a tool of transformation when it comes from these massive objects. Giant stars pour out incredible amounts of energy, sending radiation streaming in all directions. When this high-energy light encounters clouds of hydrogen gas floating in space, something remarkable happens. The radiation strips electrons away from hydrogen atoms, a process called ionization. Ionized hydrogen has a particular property. It glows with a soft reddish light. This means that giant stars can literally light up entire regions of space, creating vast glowing clouds that stretch across thousands of light years. These illuminated regions, known as H2 regions, often surround clusters of massive stars, like cosmic streetlights, brightening the neighborhood. The heating effect goes beyond just making gas glow. As the radiation warms the surrounding material, it increases the pressure, causing the gas to expand outward. This expansion pushes against everything nearby, carving out enormous cavities in the fabric of interstellar space. Some of these cavities grow to hundreds of light years across, creating hollow regions surrounded by dense shells of compressed gas and dust. Stellar winds add another layer to this cosmic sculpture. Even during relatively calm periods of their lives, massive stars continuously lose material through steady outflows of gas. These winds race outward at incredible speeds, sometimes reaching thousands of kilometers per second. When they slam into the surrounding interstellar medium, they create shock waves that compress and heat the gas. The result is a complex network of expanding bubbles filled with hot, thin plasma, each one surrounded by cooler, denser shells. In regions where many massive stars form together, their individual winds combine and interact, producing even larger structures called superbubbles. These can span significant portions of a galaxy's spiral arms. There's a beautiful contradiction at work in these processes. The radiation and winds from giant stars can actually prevent new stars from forming by dispersing the gas clouds that would otherwise collapse into stellar nurseries. But at the same time, the shock waves created by these same processes can compress other parts of those clouds, triggering the gravitational collapse that leads to star birth. So massive stars are simultaneously creators and destroyers, both encouraging and inhibiting the formation of their smaller siblings. They're active participants in the ongoing cycle of stellar birth and death that shapes the structure of galaxies. The elements produced inside giant stars represent another profound contribution to cosmic evolution. Nuclear fusion in stellar cores transforms lighter elements into heavier ones, creating carbon, oxygen, silicon, iron, and dozens of other elements that didn't exist when the universe was young. When giant stars shed material through stellar winds or explode as supernovas, they release these newly forged elements into space. This process gradually enriches the interstellar medium, adding complexity to what was once almost pure hydrogen and helium. The first generation of stars had to work with an extremely limited palette of elements. Over billions of years, successive generations of stars have painted the cosmos with an increasingly rich mixture of materials. Today's star-forming regions contain all the ingredients necessary for rocky planets, complex chemistry, and ultimately, life itself. Motion adds yet another dimension to how giant stars shape their environment. Massive stars often form in clusters, and their interactions can dramatically affect the dynamics of these stellar groups. When a giant star explodes as a supernova, the sudden loss of mass changes the gravitational balance of the entire cluster. This can send nearby stars into new orbits, or even eject them completely, turning them into high-speed wanderers racing through interstellar space. The shock waves from supernovas travel for tens or hundreds of light years, sweeping up gas and dust like cosmic snowplows. These expanding shells of material eventually slow down and merge with the surrounding medium, but not before leaving permanent marks on the structure of the galaxy. Astronomers studying our own Milky Way have identified enormous arcs and bubbles of gas that represent the combined remnants of multiple supernovas and stellar winds operating over millions of years. Most of these structures are invisible to our eyes, but radio telescopes and infrared observations reveal their presence throughout the galaxy. Space turns out to be full of cavities and filaments, all shaped by the lives and deaths of giant stars across cosmic time. Cosmic rays represent another way that massive stars extend their influence across vast distances. Supernova explosions accelerate particles to extreme energies, sending them racing through space at nearly the speed of light. These high-energy particles travel across entire galaxies, occasionally interacting with planetary atmospheres and magnetic fields. While Earth's magnetic field and atmosphere protect us from most cosmic ray effects, these particles play important roles in the chemistry of interstellar clouds. They influence how molecules form in space and affect the ionization of gas throughout the galaxy. In this way, the effects of giant stars reach far beyond their immediate neighborhoods, contributing to processes that span galactic scales and influence the evolution of entire star systems. The universe becomes a deeply interconnected web, where the death of one massive star can affect the birth of planets around completely different stars, light years away, and millions of years in the future. When we peer out into the vast darkness of space, we're witnessing invisible processes unfolding on scales that dwarf our imagination. The universe operates like a grand recycling system, constantly transforming matter and energy in ways that escape our everyday notice. Giant stars burn with such intensity that they reshape entire regions of their galaxies. These cosmic giants, though rare compared to smaller stars, create the spiral patterns we see stretching across galactic arms. Their brilliant light cuts through cosmic dust, illuminating clouds of gas that would otherwise remain hidden in darkness. The winds flowing from these massive stars carry incredible force. They push and sculpt the surrounding material, carving out bubbles and cavities in space. When these stellar giants finally exhaust their fuel, they don't simply fade away quietly. Instead, they explode as supernovas, releasing more energy in seconds than our sun will produce in its entire lifetime. These explosions scatter heavy elements throughout space, seeding the cosmos with the building blocks needed for planets and life. Without this cosmic alchemy, the universe would contain only hydrogen and helium. No carbon for organic molecules, no oxygen for water, no iron for blood. Red dwarf stars vastly outnumber their giant cousins, quietly burning for trillions of years. Yet it's the brief, brilliant lives of massive stars that drive most of the visible activity we observe in galaxies. They live fast and die young, but their impact echoes across cosmic time. The remnants of ancient supernova explosions can glow for thousands of years, creating beautiful nebulas that serve as stellar nurseries. The shock waves from these explosions compress nearby gas clouds, triggering the birth of new generations of stars. It's a cycle that has repeated countless times throughout cosmic history. Our own solar system formed from such enriched material, the debris of long-dead stars. Every atom in your body, except for hydrogen, was forged in the nuclear furnace of a star, or created in the violent moments of stellar death. We are, quite literally, made of stardust. This connection between stellar processes and our existence raises profound questions about our place in the universe. The iron in our blood was created in the core of a dying star. The calcium in our bones formed during supernova explosions billions of years ago. Time operates differently on cosmic scales. A supernova remnant visible today might have exploded when dinosaurs roamed the Earth. The light we see from distant stars shows us the universe as it was, not as it is. We're looking backward through time with every glance at the night sky. Galaxies themselves would appear dramatically different without massive stars. They would be dimmer, lacking the bright spiral arms and colorful nebulas that make them so striking. The chemical complexity that allows for rocky planets and complex molecules simply wouldn't exist. Yet even these galactic giants are merely components in larger structures. Galaxies cluster together in groups, which themselves form part of vast cosmic webs stretching across billions of light years. Each level of organization reveals new patterns and processes. Human fascination with cosmic extremes reflects something deep in our psychology. We're naturally drawn to superlatives, the biggest, brightest, and most distant objects we can find. This curiosity extends beyond astronomy into all aspects of life, from the tallest mountains to the deepest ocean trenches. Perhaps this attraction to extremes served an evolutionary purpose. Our ancestors who wondered what lay beyond the next hill or across the river were more likely to find new resources and opportunities. Curiosity drove exploration, which enhanced survival. The night sky has always inspired wonder and speculation. Ancient peoples created elaborate mythologies to explain the patterns of stars and the wandering of planets. Modern science provides different answers, but the fundamental sense of awe remains unchanged. There's something both humbling and comforting about contemplating cosmic scales. The problems that loom large in our daily lives shrink when viewed against the backdrop of a universe filled with billions of galaxies. Yet this perspective also highlights the remarkable nature of our existence. The fact that the universe has evolved to a point where it can contemplate itself through human consciousness is perhaps the most extraordinary development of all. We are the cosmos becoming aware of itself, collections of stellar debris that have somehow learned to wonder about their origins. Describing cosmic extremes comes naturally, because the concepts, while vast, are relatively simple. A star so large it could contain the orbit of Jupiter captures the imagination immediately. The numbers may be incomprehensible, but the basic idea resonates clearly. This accessibility makes astronomy uniquely democratic among the sciences. Anyone can look up and wonder, regardless of their educational background. The same stars that puzzled ancient philosophers shine down on modern city dwellers, connecting us across cultures and centuries through shared curiosity about our cosmic home. When we think about a star that dwarfs our sun by 1,000 times, the raw scale of it hits us immediately. These numbers don't need complicated explanations. They carry their own weight, their own sense of wonder. But what's really happening inside these cosmic giants goes far beyond simple size comparisons. Deep within these stellar behemoths, nuclear fusion churns away, creating the very elements that make up, well, everything we know. The pressure down there is so intense that hydrogen atoms get squeezed together until they become helium, releasing tremendous amounts of energy in the process. This energy then begins a journey that can take thousands of years just to reach the star's surface. As that energy travels outward, it creates radiation pressure, pushing against the star's own gravity, which is constantly trying to collapse everything inward. It's like a cosmic tug-of-war that's been going on for millions, sometimes billions of years. The star wins this battle through convection, where hot material rises to the surface while cooler material sinks back down, creating these massive currents of plasma. that are larger than entire planets. Then there are stellar winds, streams of charged particles that flow away from the star's surface at incredible speeds. These winds can strip away layers of the star's outer atmosphere, carrying material across vast distances through space. Some of this material eventually finds its way into forming new stars, new planets, maybe even new forms of life. What's fascinating is how all of this follows the same basic rules we see everywhere else in the universe. Gravity pulls things together, pressure pushes them apart, heat flows from hot places to cold places. Whether we're talking about water boiling in a pot or a star that could swallow Jupiter's orbit, the underlying principles remain the same. This consistency across such different scales suggests something profound about the nature of reality itself. The universe isn't some chaotic, unpredictable place where anything can happen. It's governed by laws that apply whether you're studying something as small as an atom or as large as a galaxy. There's a strange comfort in knowing that even the most extreme objects out there are playing by the same rules. Psychologists have noticed that when people contemplate these cosmic scales, something interesting happens. They experience what researchers call awe, that mixture of wonder, curiosity, and the gentle recognition of how small we are in comparison. Studies show that this feeling can actually reduce stress, make us more patient, and help us feel more connected to the world around us. It's almost paradoxical how thinking about things so impossibly distant and large can make us feel more at peace with our immediate, everyday concerns. Perhaps it's because these stellar giants operate on timescales that make our daily worries seem fleeting. While we rush through our days, these massive stars burn steadily for millions of years, their light traveling across space, long after the star itself has died. When astronomers search for the biggest, most extreme stars, they're really probing the limits of what's physically possible. How much mass can a star actually hold together before it collapses under its own weight? How large can it expand before it becomes unstable? These questions push us to understand the fundamental laws that govern everything. Every time we discover a new record holder, a star that's bigger or more massive than anything we've seen before, we learn something new about the boundaries of physics. Sometimes these discoveries lead to new technologies, new ways of understanding gravity, new insights into how matter behaves under conditions we could never recreate on Earth. The study of supernovas, those spectacular deaths of massive stars, has helped us understand that the universe itself is expanding. Observations of what's left behind after these explosions, neutron stars and black holes, have given us glimpses into how space and time behave when pushed to their limits. But beyond the scientific discoveries, there's something deeply personal about our fascination with these cosmic extremes. We naturally compare ourselves to the world around us. It's how we figure out where we fit in the bigger picture. Learning about giant stars gives us a sense of scale that's impossible to get any other way. Our sun, which seems enormous compared to Earth, suddenly becomes modest when we compare it to a red supergiant. Our planet, which feels vast when we travel across continents, becomes almost invisible from the perspective of the galaxy. This shift in viewpoint can be humbling, but it can also be oddly comforting. It reminds us that we're part of something much larger than ourselves, that our individual troubles and concerns are small pieces of a much grander story that's been unfolding for billions of years. At the same time, there's something remarkable about the fact that beings as small as us can understand these immense objects at all through careful observation, mathematics, and reasoning. We've figured out how stars are born from clouds of gas and dust, how they live their long lives burning nuclear fuel, and how they eventually die, sometimes in spectacular explosions that can be seen across the entire universe. This ability to understand, even partially, creates a meaningful connection between us and the cosmos. There's also something inspiring about imagining these places we can never visit. It's one thing to read that a star is unimaginably large. It's another to picture yourself somehow standing near it, watching enormous currents of superheated gas rise and fall across its surface, movements so vast they could swallow solar systems. These mental journeys help make abstract concepts feel more real. They let us explore distant worlds, using nothing but thought and imagination. In our busy, noisy world, this kind of gentle mental wandering can be surprisingly restful. The mind gets to drift among scenes that are distant and slow-moving, free from the urgency and stress of daily life. Perhaps most profound is the story of continuity that these giant stars tell. They form from the remnants of previous generations of stars, live their long lives, then eventually explode, scattering their processed elements back into space. Over billions of years, this cycle repeats countless times, each generation of stars creating heavier elements that become part of the next. The atoms that make up our bodies, the calcium in our bones, the iron in our blood, were forged in the cores of stars that lived and died long before our solar system even existed. We're not just metaphorically connected to the cosmos, we're literally made from it. Every breath we take contains atoms that were once part of stellar furnaces burning in the ancient universe. This physical connection across such vast stretches of time creates a sense of continuity that transcends our individual lives. We're part of a story that began with the first stars and will continue long after our sun has burned out. In contemplating these cosmic giants, we're discovering our own deep connection to the universe itself. When we consider the nature of stellar giants, something profound happens to our perspective on existence itself. These cosmic behemoths, some stretching hundreds of times wider than our sun, operate on timescales that dwarf human comprehension. While we measure our lives in decades, these stellar monsters burn for millions, sometimes billions of years, their nuclear hearts beating with a rhythm so slow it makes our entire civilization seem like a brief flicker. The sheer scale challenges everything we think we know about size and distance. Picture a star so vast that if you placed it where our sun sits, its surface would engulf the orbits of Mercury, Venus, Earth, and Mars. The light from such a giant takes not minutes, but hours to travel from its core to its surface. In cosmic terms, this represents a kind of patience that human minds struggle to grasp. What draws us to these extremes goes beyond simple curiosity. There's something deeply personal about connecting to objects so massive they bend space and time around them. When you realize that the calcium in your bones, the iron in your blood, all came from the nuclear furnaces of ancient giant stars, astronomy stops being abstract. It becomes autobiographically written in the language of atoms. The beauty of giant stars lies partly in their contradictions. Despite their enormous size, they live fast and die young compared to smaller stars. The most massive ones burn through their fuel with reckless abandon, shining with the brightness of millions of suns. They're cosmic sprinters in bodies built like marathon runners, and this tension creates some of the universe's most spectacular endings. Red giants represent a different kind of extremeness, not through mass, but through expansion. These are stars in their twilight years, swollen to enormous proportions as they struggle to maintain the nuclear reactions that keep them alive. They're like cosmic balloons, their outer layers so tenuous that Earth's atmosphere is denser. Yet within that gossamer exterior burns a core hotter than anything we can imagine. The night sky holds secrets that aren't immediately visible to our eyes. That steady red point of light might be Betelgeuse, a star so large that its surface churns like a boiling ocean, with convection cells bigger than our entire solar system. The star pulsates gently, growing and shrinking over periods of years, breathing like some vast cosmic organism. Understanding stellar evolution changes how we perceive time itself. These processes unfold over such lengthy periods that entire geological ages on Earth represent mere moments in a star's life cycle. This perspective can be oddly calming, suggesting that the universe operates with a patience we rarely encounter in our daily experience. The formation of giant stars remains partially mysterious. Even to modern astronomers, we know they begin in stellar nurseries, vast clouds of gas and dust, where gravity slowly pulls matter together. But the exact processes that allow some stars to grow, so massive while others remain modest in size, involve complex interactions between magnetic fields, radiation pressure, and gravitational collapse that scientists are still working to understand. These unanswered questions point to something profound about the nature of knowledge itself. The more we learn about the universe, the more we discover how much we don't know. Each answer reveals new mysteries, new questions that push the boundaries of our understanding further outward. Giant stars also serve as cosmic recyclers, taking the simple hydrogen and helium left over from the Big Bang and forging heavier elements in their cores. Carbon, oxygen, silicon, iron, all the building blocks of rocky planets and biological life, are manufactured in the nuclear furnaces of massive stars. When these giants finally explode as supernovas, they scatter these elements across space, seeding future generations of stars and planets. The violence of a supernova explosion defies comprehension. In a matter of seconds, a star can release more energy than our sun will produce over its entire 10 billion-year lifetime. The shockwave from such an explosion can trigger the formation of new stars in nearby gas clouds, creating a cycle of stellar death and birth that has continued for billions of years. Looking up at the night sky, with this knowledge transforms the experience entirely. Those quiet points of light become characters in an ongoing cosmic drama. Some are young and hot, burning blue-white with the fury of youth. Others are ancient red giants, slowly puffing off their outer layers in preparation for their final act. The sense of scale that comes from contemplating stellar giants can shift our perspective on earthly concerns. Problems that seemed overwhelming begin to feel more manageable when viewed against the backdrop of cosmic time. This isn't to diminish the importance of human experience, but rather to place it within a larger context that can be oddly comforting. Distance plays tricks with our perception of these cosmic giants. A star that could swallow a significant portion of our solar system appears as just another point of light, indistinguishable to the naked eye from much smaller, nearby stars. This reminds us that appearances in the universe can be deeply misleading, that reality often lies hidden beneath surface impressions. The steady nature of stellar processes offers a kind of cosmic reassurance. While our daily lives feel rushed and chaotic, stars burn with magnificent consistency, following physical laws that have remained unchanged for billions of years. There's something peaceful in knowing that regardless of human concerns, Arcturus continues its stately progression across our sky, just as it has for countless generations. Modern astronomy allows us to peer deeper into these stellar mysteries than ever before. We can analyze the light from distant giants, determining their temperature, composition, and age. We can watch as some stars dim and brighten, revealing the complex pulsations that govern their outer layers. Each observation adds another piece to our understanding of how the largest objects in the universe live and die. The ability of the human mind to comprehend these vast scales represents something remarkable about consciousness itself. Physically, we are tiny specks on a small planet, yet mentally we can traverse the galaxy, imagining the lives and deaths of stars we will never visit. This capacity for understanding connects us to the cosmos in ways that transcend our physical limitations. Giant stars remind us that the universe is an active, dynamic place where dramatic events unfold over timescales both longer and shorter than human experience. The slow burn of stellar fusion continues for eons, while the final collapse and explosion of a massive star happens in the blink of an eye. Both extremes of time coexist in the stellar realm, creating a rhythm of cosmic evolution that has shaped everything we see around us. The cosmos operates on timescales that dwarf human experience, where stellar lives unfold over billions of years. Stars burn their nuclear fuel with methodical precision, slowly converting hydrogen into heavier elements deep within their cores. This process continues for eons, far longer than life has existed on our planet. The deliberate pace of these celestial furnaces creates a rhythm that seems almost meditative when you consider it. Think about how a typical star like our Sun will continue shining for another 5 billion years or so. That's roughly 1,000 times longer than complex life has existed on Earth. During all that time, the star maintains its steady output, day after day, year after year, with remarkable consistency. There's something profoundly reassuring about this cosmic reliability, this unhurried persistence that governs the universe. Galaxies themselves dance to an even slower beat. Our Milky Way completes one full rotation approximately every 225 million years. The last time our solar system was in its current galactic position, dinosaurs hadn't even appeared yet. The spiral arms that give galaxies their distinctive shape move like cosmic weather patterns, but at speed so gradual that entire civilizations could rise and fall between noticeable changes. Even more remarkable is how the universe expands. Space itself grows larger with each passing moment, but this expansion happens so slowly that it's virtually imperceptible on human timescales. The distance between distant galaxies increases, but at rates that require sensitive instruments to detect. This gentle stretching of the cosmic fabric has been happening for nearly 14 billion years, and it continues today with the same patient consistency. When ancient peoples gazed upward at the night sky, they experienced something we can still access today. Without understanding nuclear fusion or galactic rotation, they felt a sense of connection to something larger than themselves. The stars provided a backdrop of constancy against the rapid changes of daily life. Seasons came and went, but the constellations returned with predictable regularity. Modern astronomy has revealed the mechanisms behind what our ancestors observed, but it hasn't diminished the fundamental experience. If anything, scientific knowledge deepens the sense of connection. We now know that stellar cores reach temperatures of millions of degrees, hot enough to fuse atomic nuclei together. This process creates the heavier elements that eventually become planets, oceans, and living beings. The calcium in your bones was forged inside a star that lived and died before our solar system formed. The iron that carries oxygen in your bloodstream was created during the final moments of a massive star's life, when it collapsed and exploded in a supernova. These aren't poetic metaphors. They're literal facts about your physical composition. Stars create elements through a kind of cosmic alchemy. Lighter elements combine under intense pressure and temperature to form heavier ones. Helium forms from hydrogen, carbon from helium, oxygen from carbon, and so on up the periodic table. Each step requires specific conditions that exist only in stellar interiors or during stellar explosions. When a star reaches the end of its life, it doesn't simply vanish. Smaller stars shed their outer layers gradually, creating colorful clouds of gas that drift through space. Larger stars end more dramatically, ejecting their contents in violent explosions that can briefly outshine entire galaxies. But whether gentle or explosive, the result is similar. The star's accumulated elements spread throughout space, becoming raw material for future generations of stars and planets. This recycling process has been going on for billions of years. The universe started with mostly hydrogen and helium, but stellar processes have gradually enriched space with heavier elements. Each generation of stars contributes more complex atoms to the cosmic mix. Without this ongoing cycle, rocky planets like Earth couldn't exist, and neither could the chemistry of life. Consider how this perspective changes the meaning of endings. When a star exhausts its fuel and dies, it's simultaneously giving birth to future possibilities. The scattered elements will eventually condense into new stellar systems, possibly including planets where life might emerge. What appears to be destruction from one viewpoint becomes creation from another. This pattern of transformation appears throughout the universe. Nebulae collapse to form stars, stars forge elements, and eventually disperse them, and the dispersed material coalesces into new structures. Nothing is truly lost, only transformed into different arrangements of matter and energy. The universe operates like a vast recycling system, constantly breaking down old structures and building new ones. Even on Earth, we participate in similar cycles. The atoms in your body have been part of countless other structures throughout history. They've been in rocks, seawater, plants, and other living things before becoming part of you. After you're gone, they'll continue their journey, becoming part of new arrangements in the ongoing dance of matter and energy. Human life unfolds against this backdrop of cosmic patience. We experience change on timescales of days, years, and decades, while the universe measures change in millions and billions of years. Both rhythms are real and important, but there's something calming about remembering the larger perspective. Our immediate concerns, however pressing they feel, exist within a context of almost unimaginable vastness and duration. The night sky offers a window into this deeper rhythm. Each visible star represents a nuclear furnace that has been burning for millions or billions of years. The light reaching your eyes tonight began its journey long before humans existed. You're seeing the universe not as it is now, but as it was in the distant past. This creates a kind of time travel, connecting you directly to cosmic history. Perhaps this is why contemplating the cosmos can feel so settling. It provides perspective on the temporary nature of immediate problems, while connecting us to something enduring and magnificent. We are neither separate from the universe nor insignificant within it. We are expressions of cosmic processes, temporary arrangements of stellar debris that have somehow developed the ability to contemplate their own origins. Breathing happens without much thought. This gentle rhythm that keeps us alive, in and out, steady and predictable. Stars breathe too, in their own way, though their cycles stretch across time spans that make human lifetimes seem like single heartbeats. These cosmic giants expand and contract, pulsing with a rhythm set by forces we're only beginning to understand. The largest stars, the ones we call hypergiants, are so enormous that a beam of light, traveling at its incredible speed, would take several hours just to cross from one side to the other. Think about that for a moment. Light itself, which can circle our entire Earth 7 times in a single second, struggles to traverse these stellar behemoths. It's like trying to walk across a continent where each step takes you only a few inches forward. These massive stars live fast and die young, relatively speaking. While our sun will burn steadily for about 10 billion years, these giants consume their fuel so rapidly that they exhaust themselves in just a few million years. They're the cosmic equivalent of burning a candle at both ends, brilliant and spectacular, but destined for a brief existence. Stars lose mass constantly through stellar winds, streams of particles flowing away from their surfaces like invisible rivers. Our sun loses about 4 million tons of itself every single second, yet this massive loss barely registers against its total mass. It's been doing this for nearly 5 billion years, and it will continue for billions more, hardly affected by this constant bleeding into space. The pace of stellar evolution follows laws that operate with mechanical precision, yet the results are anything but predictable. Each star's journey depends on its mass, its composition, the environment it formed in. Some stars will quietly fade away as white dwarfs. Others will explode in supernovas so violent they outshine entire galaxies for weeks. When we consider these vast timescales, our daily concerns take on a different character. That meeting you're worried about, the argument that's been bothering you, the deadline that feels overwhelming, these experiences are real and meaningful, but they exist within a framework so much larger than we usually contemplate. It's not that our problems don't matter, but rather that they're part of something unimaginably vast and ongoing. Standing under a night sky connects us to every human who has ever lived. Ancient shepherds watching their flocks saw the same constellations we see today. Philosophers in ancient Greece wondered about the nature of those distant lights. Medieval scholars tried to understand their movements. Each generation has looked up and felt that same sense of wonder, that same curiosity about what lies beyond our small world. The red giants among the stars are particularly fascinating. These are stars in their later years having exhausted the hydrogen in their cores, now burning heavier elements and swelling to enormous sizes. Some red giants are so large that if you placed one where our sun sits, it would engulf Mercury, Venus, and possibly Earth itself. Yet despite their size, many are actually cooler than our sun, which is why they appear red instead of the familiar yellow-white we're used to. The universe operates on principles that seem almost impossibly patient. Nuclear fusion in stellar cores happens through processes so unlikely that individual reactions are extraordinarily rare, yet with billions upon billions of particles involved. The overall process continues steadily. It's like having a lottery where winning is nearly impossible, but so many tickets are being drawn every second that winners emerge constantly. Stars form in regions called nebulae, vast clouds of gas and dust that span dozens of light years. These stellar nurseries are among the most beautiful objects in space, glowing with the light of newly formed stars. and painted in colors that seem almost too vivid to be real. The process of star formation takes millions of years, as gravity slowly pulls material together, heating it until nuclear fusion finally ignites. Throughout human history, people have used stars for navigation, for marking seasons, for telling stories that pass down wisdom through generations. These same stars witnessed the rise and fall of civilizations, the evolution of species, the gradual drift of continents across our planet's surface. They've been constant companions to our world, silent witnesses to everything that has ever happened here. The light reaching our eyes tonight left many of these stars years, decades, even centuries ago. When you look at a star, you're literally seeing into the past, receiving ancient photons that began their journey before you were born. Some of the stars we see may have already died, their light still traveling toward us across the vast emptiness of space. This creates an odd sort of time travel, where the present moment contains light from multiple points in the past, all arriving together to create the view we see. The night sky is like a museum, where exhibits from different eras are displayed side by side, each telling its own part of a story that spans cosmic time. When we look up at the night sky, we're witnessing something truly extraordinary. Those pinpricks of light, scattered across the darkness, they're actually massive nuclear furnaces, burning at temperatures that would instantly vaporize anything we know on Earth. The light hitting your eyes right now, it began its journey years ago, sometimes decades, sometimes centuries before you were even born. Consider this for a moment. The photons entering your retina, they've been traveling through the cold emptiness of space, carrying with them the story of distant suns. Some of these stars are so large that if you placed them where our sun sits, they would swallow up the orbits of Mars, Jupiter, even Saturn. We call them red giants, and they burn with a gentle orange glow that seems almost comforting, despite their incredible size. The nearest star to us, aside from our own sun, is Proxima Centauri. Its light takes over 4 years to reach us, which means when you see it twinkling, you're actually seeing it, as it was 4 years in the past. If that star suddenly disappeared right now, we wouldn't know about it until the year 2028. Space, it seems, has its own way of keeping secrets. Our galaxy, the Milky Way, contains roughly 400 billion stars, each one a sun in its own right, many of them surrounded by planets we'll never visit, never even see. Some of these worlds might harbor oceans beneath frozen surfaces, or atmospheres thick with clouds that rain liquid methane. The sheer scale of possibility, it's almost overwhelming to contemplate. The atoms that make up your body, they were forged inside the cores of dying stars billions of years ago. When massive stars reach the end of their lives, they explode in what astronomers call supernovas, scattering heavy elements like carbon, oxygen, and iron across space. These elements eventually coalesced into new solar systems, new planets, and eventually, new life. In a very real sense, we are made of stardust, temporary arrangements of cosmic material that somehow learn to think, to wonder, to look back up at the sky and ponder its origins. The light from the most distant galaxies we can observe, it's been traveling for over 13 billion years. When we peer through our most powerful telescopes, we're literally looking back in time, seeing the universe as it was when it was young, when the first stars were just beginning to shine in the primordial darkness. Even our own sun, that familiar yellow disk that rises and sets each day, it's converting 600 million tons of hydrogen into helium every single second, releasing energy that will keep our planet warm for another 5 billion years. The warmth you feel on your face during a summer afternoon, that energy began its journey at the sun's core, taking roughly 100,000 years just to fight its way to the surface, then 8 minutes and 20 seconds to cross the void to Earth. Sometimes, on particularly clear nights, you can see the Andromeda galaxy with the naked eye, a faint smudge of light containing over 1 trillion stars. It's racing toward us at 250,000 miles per hour, though don't worry, the collision won't happen for another 4.5 billion years. When it does occur, the two galaxies will merge into something entirely new. A cosmic dance played out over millions of centuries. The silence of space, it's profound in ways that are difficult to imagine. Sound waves need matter to travel through, and in the near-perfect vacuum between stars, there simply isn't enough of anything for sound to exist. The explosions of dying stars, the birth cries of new worlds, the collision of galaxies, all of it happens in absolute silence, a universe-wide symphony that plays without making a sound. Perhaps what's most remarkable is that in all this vastness, in all these billions of galaxies containing billions of stars, we know of only one small blue planet where life took hold, where simple chemicals organized themselves into something capable of contemplating the very cosmos that created them. Whether we're alone or part of a larger community of thinking beings scattered across the universe remains one of the great unanswered questions of our time.